So, for those of you who don't know me, I'm the third name up there. I'm Christopher Geib, and that's Reuth. And Sarah's, turns out, subject to the whims of certain airline things, got delayed. And so she's not going to be here. We're sad about that. But there you have it.
Maybe later today, this evening, if you're doing dinner
Yeah,
plans, we'll
yeah,
we'll
we'll organize something. So I will also, in case it's not immediately obvious. I have, and Reuth also has a very sort of social demeanor and likes to have questions. And so if you have questions as we're going through, just, raise your hand. It's fine. We like that. That's a good thing. It leads to discussion, and that's positive. And that's what these things are all supposed to be about. It's about, learning more. Um, do I have anything else I want to say about that one? I don't think so. Uh-oh. Oh, that's upsetting. There you go. The pictures of all of us. So, but you know what we look like. So now you know what Sarah looks like. You'll see her around. She'll be here. Okay, what are we doing here? We're talking about plan activity and intent recognition, we need to change the name of that because we got to get rid of that intent in there. But okay, anyway, doesn't matter. I have a whole rant about that. You'll hear me rant. It's not a problem. Don't feel like you're missing out on something. Um, the general structure of this is there's a historical overview, and then we're going to talk about formulating plan recognition problems, and we're going to talk about solution approaches, and then we've got a slide, and we hope people will very much want to talk about that a little bit about some open challenges and what we see as the open challenges here, and what maybe you think the open challenges are still. So, uh, right. You, whether you know it or not, are now part of a very long and very storied tradition of plan activity and intent recognition research. That's what you're looking at. There are images that we had. We organized pair in 2017, all kinds of different workshops and sub-conferences that we've had over the years. I was joking before about Moo, which was modeling others from observations, which was the forerunner series of things, and that happened for like 2 or 3 years. And then, God, we've been doing this for a long time now. Not every year, but it happens. So,
and the book
oh
that
yeah,
you wrote, inspired by this tutorial that we gave 5 years ago. It was published in 2021, and if you really like this and you're interested, you can go through the QR code and buy it. And also, Springer are here, and there are 3 copies of the book. If you want a signed copy, this is the
A, you can get a signed copy, very exciting. B, if you want one, run right out and buy one there because, your other confreres here might get there first, and you don't want that, right? You want to get one of the copies. So I would go right over there as soon as you can and say, "Hey, I demand my copy of Introduction to Plan." That's not what the cover looks like, is it?
They've changed.
They changed the cover on this. Okay, well, there you go. That's not what the cover used to look like. So there you go. Anyway, as Reuth was saying, we did this tutorial a couple of years ago. It inspired the book, and we're doing it again. And it's updated, and there you go. Okay, so why am I here? I like to joke. I didn't have a beard for a very long time, and I like to joke about the idea that I couldn't be an old gray beard until I had a beard, so I had to grow a beard. And the problem is that once I grew my beard in, it was already gray. And I was very sad about that fact, but that's the nature of it. The real reason that I'm here is to do historical overview because I've been doing this for a long time. And sadly, I remember when many of the papers we're going to talk about were actually first presented. And sadly is because you'll see some of the dates. But anyway, um, for those of you who don't know, if this is the first time you're learning about plan recognition or at all, we were there at the beginning, man. This is one of those. This is we're the problem nobody talks about that was really there at the very beginning when AI was first started, right? At the Dartmouth Convention back in '56, right? This is eons ago, right? when they first coined the term artificial intelligence, they were already talking about plan recognition. That was one of the topics that they listed in the proposal that they wrote. 59, you see Newell, Shaw, these people, they built the first generalized problem solver. If you've ever heard about that, this is what kind of invents means ends reasoning at an algorithmic level for AI. Then we've got, this is a really important one for us, is 1960, the plans and the structure of behavior. Um, and we're actually formulating this and we're starting to actually, it's a collection of a whole bunch of stuff that never really got published anywhere else, but it's fine. It's great. So that's, we're starting to get into actual structured plans, and that's great. We love that. Then, for those of you who remember your first AI class strips, 71, right? Then, and now this is where it gets really exciting for us. 78 is plan recognition, the plan recognition problem, an intersection of psychology and artificial intelligence. This is the first serious published plan recognition paper that you will see if you go looking for this. And you should really, I will say very little bit about the people who work on hidden Markov models and Markov reasoning, because they were here even before we were, which is crazy, right? Back in the 30s and 40s, depending on how you think about um, plan recognition and what it actually is. It's arguable that back in the 30s and 40s, these people were actually looking at the problem. So, and I'll say a little more in just a bit. Oh, and if I'm going slow, speed me up because I didn't look. Oh, I gotta watch. I'm good. This this is out of that first paper that I quoted you. The problem of plan recognition is to take an input as input, a sequence of actions performed by an actor, and to infer the goal pursued by the actor, and also to recognize the action sequences in terms of a plan structure. Plan structure explicitly describes the goal sub-goal relations among its component actions. So this is the first time somebody actually says that about the plan recognition problem. What it means that you have to actually have this formal structure, that you have to be recognizing the goal, that you're taking a set of input actions as your inputs, and that that's our objective, right? First time we formalized this, that's in 78, was it? Something like that. So. Okay, so now let me digress a little bit. That's setting the stage on the history, but let me digress a little bit about the problem because it turns out, like many of the subfields in that were enumerated at the Dartmouth conference about that we wanted to study in AI, it turns out that there's a lot to unpack here. That we thought it was going to be really easy, and we thought that we knew what we were talking about, and it turns out we hadn't formalized anything, and we didn't really know anything. It turns out that there are a bunch of subproblems here. And especially if you start to read the early work, which you should do, um, you will get quickly confused because they will use the same term to refer to different problems because they hadn't formalized them. They hadn't talked about what they were and how they were different. There are at least three different problems that have all at one time or another gone by the name plan recognition. One is what now we think of as activity or behavior recognition. This is sort of the lowest level that you might think about. Then there's goal recognition, and that's sort of the highest level of the inferential process that you're talking about. And then there's what I think of as plan recognition, and the previous quote talks about as plan recognition, wherein you're doing this middle work, you're building a structure, and you're inferring the goal, and maybe, or maybe not, doing activity recognition. So I personally think activity recognition is really the input to plan recognition. But there have been lots of papers where people will tell you, oh, I'm doing plan recognition. And what they're really doing is something more like activity recognition. And I'm going to define all of these terms, so don't panic. Okay. Guess what? I've just realized that the titles of all of our slides are not showing up. Where's our, yeah. So this is activity recognition. Yeah, see, it's supposed to say at the top activity recognition, which would make it a whole lot easier to actually understand what my slide was. This is a definition for activity recognition. So the input that you're getting, yeah. Are they coming? Ah, are you here to help us?
Of course.
The title of my slides is not showing. So there's a top little bit on the slides that is not. Is there a way to, maybe we push the whole thing back? I don't know.
Uh-huh.
Because otherwise you're going to lose the bottom. Oh no, it's being clipped by the software. Because you can see the OK button.
Yeah.
So I don't, that moving that isn't going to help us. Okay. Well, I'll talk a little more while he's running away. So this is activity recognition. And the idea, really, the fundamental question when you're talking about activity recognition, oh, he's back already. And I shouldn't have gotten started. Oh, just to grab his phone. Led me astray. Right. So you're going from a sequence of noisy sensor inputs over time. So this is raw sensor inputs. And the output really is a unique label for each temporal sequence. So I've got a set of inputs that I'm getting from my sensors. They're over some time window. And what I'm trying to do is label that sequence and say, this is the thing that's happening here. Someone is playing soccer. Someone is, I don't know, fueling an airplane, thinking of papers. um, or just walking, hopping, brushing their teeth, something reasonably small. So, excuse me, the central problem here really is getting from noisy inputs, noisy sensor inputs, to a name, to a tag, to uh, uh, a thing, something I can reason with. They might be structured, they might not. Depends. Usually it's just a label. Another alternative characterization of this is behavior recognition. Lots of people call this behavior recognition, and that's okay too. We can have a debate about whether something's an activity or a behavior, and lots of people do. Oh yeah, you got a question? Yes, be a classification task for time series off real sensors. Yep, exactly right.
Sometimes it includes segmentation as well.
Yeah. It can include segmentation so that you're actually separating. You want to be able to say this is one activity, this is another activity, that's a third activity. So yeah. Video segmentation of football plays, classic example. We'll talk more about that in just a little bit. Okay. Goal recognition. How is goal recognition different? Well, goal recognition is this: you take an ordered sequence of discrete symbolic input tokens and you get a unique label. Sometimes you get it with a probability, sometimes you don't. Sometimes you do activity recognition with a probability, sometimes you don't. Anytime I say it's gonna have one, someone's written a paper where it doesn't. So be forewarned. But you're again trying to label that sequence. You're trying to come up with a label for the whole sequence that says this is what's happening here. And the fundamental idea here, the fundamental problem that you're actually characterizing, or the central problem that you're trying to solve, is actually dealing with the evidence from the multiple input tokens. Like given that I saw somebody pick up a pot and filled a pot with water, what's their high level goal? Their high level goal. That's, oh, they're making pasta, something, right? Yeah, so there you go. I really love this example, identifying computer user goals from observing their actions. It's a really great, famous example that we'll talk more about in a bit. But lots and lots and lots of systems are interested in telling someone what the goal of a particular user is at a particular time. And so you'll see that all the time. So goal recognition. Okay, I've now given you, yes.
Right. You think that I'm going to already discrete symbolic, discrete symbolic. I'm curious. We can use the goal definition for the sequence of the continuous
Yes, you can sometimes. And what you're pointing out, and that's really important here, is that in fact, and Sarah and I have this argument a great deal of time. Actually, we agree about this particular fact, which is one person's activity recognition can be another person's goal recognition. And it really depends, some people will say, "Oh, no, that's a goal and you're done." Because I've decided that's a goal. And some people are like, "No, no, 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 I'm interested in this contributing to something later. And therefore I want to think of it as activity recognition." And so, yes, you can definitely do goal recognition from continuous sensors if you want. That's certainly a possible thing that people do. There's a really great paper. Am I going to pull the site? No, that one's lost. But it was video streams of aircraft on the ground at an airport, and they were trying to figure out what was going on this aircraft is being refueled. This aircraft is being uh, uh, having the luggage put in it. Very high level goals for what was going on. Really temporally extended sequences of things, and they were doing it from continuous video. So yeah, yes, you definitely can do goal recognition from continuous stuff as well. So yeah, there you go. Okay, well, we better stop.
So I'll use this opportunity to add, I think that often the difference between goal and activity is why do you care?
Yes. Yeah. Yeah. What is it you're trying to do with the output? If you're going to combine your outputs into something bigger, something more, yeah, it's probably activity recognition. If you're just using it to bias something else later on, oh, I believe I really do know what they're doing, and so I'll give them this advice, maybe. That's more like goal. Um, sorry. No, no, it's I can keep going. That's fine. Okay. So okay, you're gonna change it.
You tell us if you want us to do it later or.
No, it's fine. It's better to get I need them. I need the tops for the later slides. I can do this part from memory. Yeah. No, it turns out that there's a whole black bar on the slides that's above this that has a title on it. And when you tip the thing down, which he was doing earlier, you push it back out, you can see the button. This is getting clipped by whatever viewing software they're using.
The meeting is being recorded. Okay, banner. I think that's how.
Oh, is it? Can you? Oh, okay. I can't see that.
The cursor navigates there on the screen.
Where?
A little bit south, a bit higher,
A little higher. It's a community project.
northwest.
No. You got an idea?
Yeah.
Now, if you look very up high, you see that it's glorified.
Oh, there you go. Now we just need to tip the whole thing down.
Here.
Oh, see, I couldn't even see that where I was standing. Okay, there you go. That's what we need. Keep going, keep going. There you go. Brilliant. Brilliant. That's what we needed. Yay. Thank you. Thank you. Great. Okay. That's even better. Up just a little, because there are going to be things at the very bottom. Stop. Yeah, because that's the edge. Nope. Up just a hair. Don't worry. Stop. Suppose that is. There, we've got the whole slide. You can see the number and everything. Love it. There we go. Okay. So this is goal recognition, right? Great. Okay, so now I've described the top, I've described the bottom, and now I'm going to tell you what plan recognition is. That was all by way of setting this up, right? Plan recognition is you're combining that goal recognition bit, right, with building structured representations of what's going on in the plan, where you are in the plan, what things have been done, what things might happen in the future, what things would, if this plan continues, where are you going to be, right? So you take in, like we discussed with goal recognition, you take in this ordered sequence of discrete symbolic input tokens. And yes, you might do it with continuous stuff, but you have to segment it up. And all these things have caveats, right? But what you're getting out crucially here is a complex structure. It is not just a label. It is a structured representation, frequently involving hierarchy, frequently involving causal connections between the actions that you're observing and that you've seen, and abstract actions or abstract tasks, then subtasks, and all that lovely complexity that we actually want to reason over. So there's a reason that you actually want to do this. You want to do this so that you can actually see what's going to happen, or predict what's going to happen in the future, not just what's happening now. So you're combining these. The central problem then really is combining sequences of lower level observations into these larger causal structures. Okay? And patterns. And it might be probabilistic, it might not be. There are lots of different approaches to this. One strange thing that you might not think of it this way, but if you think about it long enough, you'll realize it is this way, is you're really doing temporal pattern matching is what's going on. It's a complex pattern that you're recognizing with a structure, and that's what you're doing. So it's this complex temporal pattern matching. And there is an element to which you're doing sort of sequence matching, or and we'll talk a lot about this, sort of the classic old school idea of building a parse tree. It's very, very similar to what's going on here. It's shockingly similar. One of my very favorite examples, paper I wrote years and years and years ago about identifying the plans and goals of cyber intruders and their progress through a network. And why can you do that for this? Well, it's actually turns out it's really easy, because when you have cyber events, they're discrete logs. So the activity recognition problem almost goes away, right? If you see something in an event log for your security system, that thing happened. All of the activity recognition has gone away. So now you're just working with those symbolic tokens and building plans and building larger structures about what's going on. But it's horribly, lovely, wonderfully complicated, because no hacker on the planet does exactly one thing at a time. They do lots of things at a time, and that becomes tricky. That's when it gets fun. So, okay. Now oh yeah. So it already involves, I'm sorry, I didn't catch the last. Yes. So the idea is that you have a structure that you can predict from. Yeah. Yeah. Yep, exactly. So you're actually adding structure that allows you to do prediction. You can do prediction with goals too. I mean, the Markov people have been doing that forever, right? This is the last token, what's the next token? And the number of people, LLMs, I'm looking at you, that are doing next token prediction from the last token. Yeah, you can do that. They've got a sequence before, but yeah. But yes, very much. Okay. Yeah.
So when you're making these definitions, can you, as part of this, do you ever take into account the idea that there might be multiple plans being executed?
Oh, yes.
Same.
Oh, yes. That's when it gets fun. So the very early work, I'll talk about it. I'm gonna go back through some of the very early work, thought about it, and then everybody abandoned it because it was really hard. And then we brought it back. And so it's much easier if you know that someone is doing just one thing, but we never know that. And the number of times that people actually do just one thing is shocking. And I'm getting ahead of myself, but one of the coolest problems in the world, and I still don't know an answer for this. Oh, I don't even know if it's on our future direction slide, because it should be on our future direction slide, is if you have multiple goals, say you're doing the laundry and doing the dishes, there are actions you have to do that are not part of either one of those plans that are utterly critical for you to do the combination of the plans because you have to walk back and forth between them, right? And it's nightmarishly hard. It's amazing. It's so much fun. It's just incredibly cool because none of those actions, like I'm saying, those connective actions, those interstitial actions don't play a part in either one of the canonical representation of either one of the plans that you might think of. But yeah, multiple goals, multiple plans, exactly the kind of thing we want when we're doing really complicated things. Yeah, there you go. Okay. I got one digression here because this is a pet peeve of mine, and you need to understand that where this came from was uh, everybody for about 20 or 30 years talked about intent recognition. Intent recognition is evil. Intent recognition is anathema. Intent recognition is not what you think it means, or what anybody ever says it means when they use it. It is a bad word. If you see people talking about doing plant intent recognition, you should immediately ask yourself, what are they actually doing? Are they doing goal recognition? Are they doing activity recognition? Are they doing plan recognition? Are they doing something else? They might be doing something else. You have no way of knowing. This is a wildly poorly defined word, and it is a word that has had multiple meanings, and we have never managed to actually reduce that to a single agreed upon definition. And why this is a problem um, is that they generally, when people say intent recognition now, they don't mean what we're talking about here. They don't mean inferring a plan. They don't mean inferring an individual activity. They don't mean inferring a goal state that you're trying to get to. They mean something really weird and other. So lots and lots and lots of civilians, that is by which I mean non-AI researchers, will tell you that an intent is some kind of ineffable magic thing that, differentiates synthetic agents from non-synthetic agents. Okay, they're allowed to believe that. That's fine, but that's not what we're recognizing. Um, there was a long time where there were a bunch of philosophers who debated about how one would want to actually formalize some of these ideas, and they had two different models for this. One was that you might have a separate pro attitude, right, that I could predicate of my goal, that I intend this goal, and it's a magic other thing that's part of my logic, and I can reason about the fact that you intend something and that you're doing other things. Okay, that's fine. There's no problem with that, but that's not what we're talking about. Um, there's a different philosophy camp that believes that intention is something like, it's a state where an agent believes a particular thing, believes about that an action will cause a thing. They want that thing to happen, and therefore they are committing to actually doing that action in furtherance of that goal. Okay, again, it's a perfectly fine thing to have and to formalize, but it's not the problem we're solving. Where you get into a lot of trouble, if you actually wind up talking to anybody who's in the military, they will talk about commander's intent. And now you're in trouble because this is whatever the senior officer wanted to have happen, however poorly actually formalized it was, but that's what they wanted to have happen. And you definitely do not want a part of that problem. Trying to figure out what it was he secretly thought or she secretly thought they wanted. So just make me happier when I review your papers. Don't use the word intent recognition. That's just going to make, I'm going to have to spend more time figuring out what you're doing, and it's going to be confusing. So done with my little rant, my little tirade there. Okay. Now I'm going to talk. Okay. Any questions about what I've said so far?
One step back.
I'm too loud.
Echo.
I'm too loud. Okay. There you go. Any questions about what I've talked about so far? Okay. So now my section is the graybeard section. I'm the one who's supposed to tell you about all the kind of past work and what was cool about it and what wasn't cool about it, and try and convince you that it's actually exciting to go back and read these papers because they tell you a huge amount about where we started, the problems that we actually do already have answers to so that people don't have to reinvent those answers, and what was wrong about, what they did. And it utterly crucial to situate what you're doing in that context so that, when I get your paper to review it or somebody else gets your paper, they don't say, have you read this paper? Because you're doing something that someone else has already done. Okay. first really big paper that kind of is a classic in AI, particularly, not psychology, not, kind of the formative, not the early formative stuff, but the first paper that anybody is ever going to cite for you that they're going to hand you when they say do plan recognition is Couch and Allen. Henry Couch, James Allen, both giants. And they did this, they built this generalized plan recognizer. And it's the proceedings of the conference that foreruns this one, right? This was the AAAI before AAAI was AAAI the way it is now. What did they do? They had what was the domain they were working in? They were working in cooking. Everybody loves cooking. I don't know why there are so many papers in plan recognition on cooking. Everybody loves it. I think it's because it's a pleasant topic and it's complicated. Plans for cooking are complicated. They have temporal ordering issues. Don't put the pot on the stove before the water's in it. That's not going to work. That if you do that, something your plan's broken. I don't know, but lots and lots of work on planning for recipes and planning for cooking. This is the first paper. So again, seminal in that way. Here's the trick. They did minimal graph covering. So they had a pre-existing plan library. You're looking at it. That's what that picture is. This paper is so early that we didn't have formalized representations for Andor trees yet. That's an Andor tree. It doesn't look like an Andor tree to you and me because it doesn't have the little arcs, but that's what that is. It's an Andor tree. Let's see. The big fat arrows are alternatives, alternative decompositions, and the narrow arrows are ands. So those are the fat arrows are ors and the narrow arrows are ands. But yeah, so you have this action hierarchy, you have this plan hierarchy that you've already pre-enumerated. And with that in hand, you can do basically just graph covering. You get a set of observations in, you put those down, and you start building these structures on top of it, right? To say, well, what's the minimum graph I can actually use that is consistent with my action hierarchy and covers the set of observations? So it's great. It works. It's not horrible. It does have, it actually does. It did consider multiple things. You could be making fettuccine Alfredo and making bread. It had no problem with that. That would work just fine. But it did have this kind of weird problem and if I was there and I was doing it, I would have probably made the same assumption, which is it assumed you wanted the smallest such plan. So the smallest structure you could have. And what that meant was that if you had a plan, or if you had an explanation that had two goals, and you had an explanation that had one goal, that no matter how likely the plan for the one goal was, or how unlikely the plan for the one goal was, you would think that was the right one because it explained more of your observations at a single go. It's not a bad assumption to make, but it's not a great assumption to make because what you really want to do is something probabilistic that says, oh, hey, wait, sometimes it is more likely that I'm making fettuccine Alfredo and garlic bread than that I'm building a nuclear reactor, right? That's just, even if it's all consistent, you don't want to consider that. So great work, amazing work. Everybody should read it. It's seminal. You also need to understand that a lot of plan recognition work came out of early efforts to understand natural language. So Diane Lippman and Sandy Carberry did amazing work, just absolutely amazing work very early on in the early 90s and late 80s. Did amazing work on formalizing plans using logic and trying to do inference over those logical forms in order to actually using the situation calculus. How many people even know what the situation calculus is? No one has ever even heard of the situation calculus. Wow. Okay, cool. That's a whole nother class. You need to know about the situation calculus. The situation calculus was an effort by people very early on to formalize everything into a logic that you could actually reason about one situation to another situation. And situations became a first order element of it. I've not nearly enough time to talk about it here, so we're not going to. But the point is, you should read up about it. It's cool. It was helpful.
Opportunity for work on the domain models for LLMs.
Yes. Yes, exactly. Okay. That wasn't a question. I thought it was a question. Okay. So The real problem that they realized out of this was not that you couldn't do it. You could do plan recognition just fine. It still had some of these problems because this wasn't probabilistic work. You still had some problems with the probability things we were talking about already. But the real cost here was the encoding, the inference, because you were building enormous plan libraries and you were building enormous sets of rules that you needed, and then you had to do inference over them. And so that was very slow, right? It just was. And I had a long conversation with Diane Littman one time about why she got out of doing this work, and she was like, encoding the knowledge, man. That was the problem, was just encoding enough knowledge. So this little stretch of text here is you're inducing a plan for one clerk to help another person, given that the person requested something, and the surface structure was that the person said something, and then there was an inform act where the clerk was informed by the person that they wanted something. They wanted I don't even remember what it is. But it's a sequence of inferential steps that you have to do in order to get there. Right. Cool. Okay. It's amazing work. You should read about it. It's really fun. But it's all about discourse and how to understand what it is people are talking about in terms of the plans that they're engaging in. Okay. Mark Verlaine, giant. Reuth will tell you that I wrote the first paper about plan recognition as parsing. That is not true. Mark Verlaine wrote the first paper about plan recognition as parsing. The problem so this is formal parsing of the kind you're used to seeing if you take your favorite compilers class, right? This is LR1 parsing, right? You're using that to build the parse tree, the structure that you need, the plan structure that you need in order to understand the set of observations. I got a set of observations. It's no different than having a set of tokens. Hey, I could just parse this, right? It'd be cool. So Mark actually wrote this wonderful paper about the idea that one could do this, that you could use parsing technology for plan recognition. And he talked about parsing formal plan grammars. So this is the first person to actually say, hey, you know those plan hierarchies that Kautz and Allen gave us? We could capture those things as formal grammars. And if we captured them as formal grammars, then we could do this kind of parsing and life would be really cool. Biggest problems with Mark's work, no domain, no real application, which is upsetting. And he didn't actually provide a system. He just really said, hey, this is really parsing. You could look at it that way. And complexity results from parsing therefore apply. And that's kind of important. But he did make one really key observation, or what I think is an absolutely key observation, which is imagine that I could give you this grammar. I could give you that plan structure, that plan library. If it doesn't have recursion in it, what does that mean? Do you immediately tweak to what the problem is? You need to have recursion in there for the yield of the grammar to be anything more than a fixed number of plans. If you don't have recursion in your plan hierarchy, it can't be I can enumerate for you the set of possible plans that somebody can be following. And if I can enumerate the set of possible plans that somebody can be following, I can use string matching to do plan recognition, and it's really fast, right? I mean, we've had spell checkers for time out of mind, right? You can do that. You can use that technology to do plan recognition because you have a fixed set of plans that you're actually trying to talk about. You know and can enumerate the set of all possible plans that someone's trying to recognize. This is another thing that's a real beef of mine when people give me plan recognition papers and they say, we want to recognize these 23 plans. And I'm like, that's not hard. That's not interesting. That the 23 plans, I can do that with table lookup, for God's sake. That's not, ugh. Anyway, Mark pointed this out. You have to worry about it. So there are easy versions of plan recognition, and then there are hard versions of plan recognition, right? Okay, then we get to Robert Goldman and Eugene Charniak. Seminal paper. These are the first two guys to actually do probabilistic plan recognition. And they say, hey, we want to understand stories. We're going to read stories, and we're going to understand those stories in terms of plans that people are executing. Hansel and Gretel have gone into the woods. They're trying to collect wood. That means they're going to go home at some point. Uh-oh, they don't make it home because they meet the witch. And the witch, what's the witch's plan? The witch wants to eat them. That's a bad thing. Okay. Wow. I don't know where that came from. Anyway, Hansel and Gretel example. What did they do? How did they do it? They were doing dynamic base nets. They were assembling base nets on the fly to actually build the inferential structures that they wanted to build, and to then infer, given this set of observations, what's the most likely set of plans that you're following? What are the root goals that you're engaged in? Huge contribution. If you care about these kinds of things, they were talking about universal quantification and unbound variables in the stories, which is this nightmarishly small detail that turns out to be the linchpin of the entire story understanding problem, because you need to know who's doing what at what times. And you can't enumerate the set of all plans the way I was just talking about with Verlaine, because you need those plans to be general enough that if it turns out it's not Hansel and Gretel that go into the wood, but it's Hansel and somebody else, you don't care that it's Gretel, right? You need to be able to swap in and out the people, and that's great. The real limitation for this thing, it comes back to multiple plans and probabilities. These are the first guys to actually say, hey, wait a minute. If you have, it can be the case that two plans that you engage in these two plans at the same time is far more likely than you engaging in one plan. And that's counterintuitive, but it's true. And there are lots of examples of it. So they're the first people to come up with that. Their real problem, the hard part, of the thing that was the limitation for them, was that, keep in mind, this is 92, right? Bayes nets are introduced in 85, I think. So this is 6 years, 7 years after Uta-Pearl comes up with Bayes nets. So these are people using cutting edge tech to do this thing. And yeah, inference in Bayes nets at the time was shockingly slow. It was really hard to do. We didn't have the great efficient algorithms that we have now. So that was their problem. Interestingly, not in an AI conference, in a statistics conference. But there you go. Oh God, I gotta speed up. Okay. Pinedaf and Wellman, really cool. They also talk about plans using formal grammars, probabilistic state-dependent grammars. So these are the first people to actually combine probabilities and grammars, which is really nice. And they do some really great work. The really fun part about it is they're talking about lane changing. So this is a fun application. It's a neat domain. We're getting much closer to real world application of the problems, right? And that's kind of fun. The real limitation, I still feel like, is that they built their own probabilistic algorithm. They never followed up with it. They never actually made it freely available to everybody. And now nobody knows how their system works. So you have to talk to David or Michael and figure it out. And you can, but anyway. But right. So they had a grammar, then they took the grammar and formalized it as Bayes net, and then anyway, doesn't matter. Cool paper, mostly for the application, if you ask me. Anybody recognize Clippy? Clippy does plan recognition really badly. Really badly, right? Really kind of, well, okay, in fairness, Clippy as deployed did goal recognition. Clippy as deployed did not do plan recognition. You could talk to Eric. I think he's going to be here. I saw he was talking somewhere else. Eric Horvitz is, I think, well, he's not here yet, I'm sure. Why would he? Anyway, the point is, you could talk to these guys as they originally built the thing. They did plan recognition. They had these complex structures. It was amazing. And then the Microsoft people said, no, we don't have enough compute cycles on the laptop to run this. We're going to have to, pith this thing and make it do something much dumber. And that's why Clippy failed. Is not that the science wasn't cool, but the deployment was crappy. So that's a solid lesson to learn. They, again, were using Bayes nets. Those were very limited. They're still, because this is only 98. So, we're making progress with the Bayes nets at this point, but still it's a problem. So anyway, there you go. So software assistive agents, there's a great application for plan recognition, right? And trust me, you need to do more than goal recognition for this problem, as we all know, because Clippy sucked, right? Okay. Oh, wow. I wonder what happened there. Well, doesn't really matter. Christine Canetti and a bunch of people did really cool work in 97 about recognizing the plans and goals of students in educational settings. This is incredibly important to do plan recognition as opposed to goal recognition or activity recognition, because you have to understand what the student's doing wrong. If you don't understand the plan they're following and how that plan can be wrong, then you can't help them. You can't give them advice. You have to do plan recognition for this, right? They had explicit models of incorrect plans. Genius. Who puts incorrect plans in their plan library? Why would you do that? No, you do it for exactly this reason, right? I wouldn't normally want to infer incorrect plans. That would be a bad thing to do in plan recognition settings. But for pedagogy, for teaching, you have to. You have to. And it's a great idea. Amazing. Right. Oh, didn't go. Oh, have to close the window. Come over here and say, okay. That figure was a very complicated Bayes net figure, is what it amounted to. I don't know why it didn't show up in our slides. Okay, this is me. What am I going to say about this? Not much. It's probabilistic. It uses grammars. It's very cool. The real innovation here was this was a fully Bayesian model of plan recognition. We had these pending sets, and it really functioned like how many people are serious Bayesian people? Did anybody know about ball and urn tests? You remember this from your initial statistics class where you got a big urn and you got different balls in them? It's ball and urn sampling that we're doing to recognize plans. That's all it is at a certain level. But the trick is we combined it with efficient grammars for parsing. This is very much like the kinds of conversions that you see in a compiler's class where you rewrite your grammar to make the parsing easier. So it has a particular structure to the grammars that we used, and that was great. So yeah, now we make it all the way to 2009. We're almost current. It's exciting. Oh, we're going to talk a lot more about this one. This is another piece of, it's a packed tree, and so you have a more efficient data structure for recognizing. So there you go. But Reuth is going to say a lot more about that. This is incredibly cool. It's the first paper where anybody used a video game as their domain for plan recognition. It's amazing. They were doing rush football. Now, it's not that cool that you use a video game. Everybody uses a video game now. Not everybody's using a video game back then. But what's more important and far more important about this was the algorithm ran fast enough that you could actually give advice in real time. And that's huge. That's huge. Now you can actually give people the advice they need when they need it. And before this, the algorithms were all just way too slow to do that. So huge step forward. And Gita and David and Kevin, I didn't even remember. I love that work. Anyway, the biggest problem was putting in new plays. How do you put in new plays? It was a complicated encoding scheme that they needed for their plan hierarchy and their plan structure. And that was really tricky. You had to compile it so that it did inference really quickly. But yeah, really fun. Okay, and we're going to say a lot more about Ramirez and Geffner. So do you want to add text? No, I don't want to add text. Go away. It's not going away. Got it. Okay. I take some of the blame for this. I'm willing to take some of the blame for this. I had a conversation with Hector Geffner in about 2007, and I explained plan recognition to him, and Hector said, no, you could just do that with a planning algorithm. And I said, no, you can't do it with a planning algorithm. He said, oh, yeah, you can. And I said, no, that's a bad idea. He said, no, it's a great idea. And they ran off and, did it. They took international planning competition domains, and Hector would disagree with that. So don't go telling Hector, hey, I heard you had a whole conversation with Chris. Don't do that. It'd be bad. This is just me talking. The international planning competition, big competition on planning. They have lots and lots of domains available. And the approach here was basically you use a planning algorithm to tell you what are the acceptable tracks that if you enumerate the set of goals you can be trying to get to begin with, you build the optimal plans and you compare what you've observed to the optimal plans. Brilliant idea. Absolutely brilliant idea. Really great. Especially if you have a hammer that is a planning algorithm and you would like to do plan recognition, as opposed to coming up with a new algorithm to do plan recognition. You just want to keep using your planner? Great. There is a subtle problem here, which you may or may not notice when you think about it as I give you the set of goals, I compute the optimal plan, and then I compare to that is you're really just doing goal recognition. You're not actually doing plan recognition because you're actually comparing to the closest sequence. You're not getting a structure. This is much more like goal recognition, at least the first work. Later work, very different story, but there you go. So again, you'll hear lots of people talking about plan recognition as planning. If you're reading in the literature, and that's the paper. Okay, and now I really should be going because we're already an hour in. How long do I have? We got 2 more hours, right? Yeah. Yeah, we're good. Okay. I just love this. This is not a hugely cited paper, but I love this paper. They were doing 2D navigation and they were using hierarchical hidden Markov models, which nobody was doing at the time. They came up, they were like, hey, let's use hierarchical hidden Markov models. We'll combine those. And you can sort of, if you kind of turn your head and squint a little bit, you can sort of think of the kind of plan hierarchies that, Kautz and Allen were using as these kinds of hierarchical hidden Markov models. They have structure, there's goals and sub-goals, and you can imagine probabilistic relationships between them, and you can kind of see it. They formalized it. And they actually got it to work. This is really cool. Just wonderful. And it does give you the whole structure. You can tell where you are. You get distributions over all levels of abstraction. It's brilliant. You do have to have fully grounded models. So can't do anything with first order anything. That's a little bit of an issue. And if you want to do multiple plans, you have to enumerate that in the hierarchical, in the HMM that you're using, the HHMM, right? You have to actually enumerate the set of all possible groups of goals you can be doing at one time. Now, if all you're modeling is a person, that's not so bad because most people don't actually pursue more than about 4 goals at a time. So you could imagine having a bound on that and enumerating it, you'd probably be okay. If you're interested in an organization of any meaningful size that has lots of different things that it's trying to do, yeah, it gets to be a problem because your HHMM is just enormous because you have to enumerate all the possibilities for all the goals. And that means enumerating all the subplans, that means enumerating all the alternatives, and that means you can imagine it just gets really big really quickly. But they did it, and that's cool. They formalized it and it worked. This is just a quick nod to a really great piece of work on activity recognition. This is Henry Kautz's back, and much later, doing some really, really neat work. This is the first piece of work I know of using your cell phone. They were using location-based, might not have been cell phones, it might have been just GPS trackers that people offered to carry around with them. But they were using actual data, real data from real people, and they were inferring important activities that they were doing from the GPS trace, the activities they were doing, and the significant places in their world. And now our phones do this every single day, all the time, for us for free, right? And this is back in 2005, and they were doing it, and it's very cool. Very cool stuff. I said before I was going to promise you a small nod to the Markov decision process people. They were here like in the 50s. They were actually thinking about predicting the next state, given the set of states I've already been through, and saying, how many states do I get to look back through? Do I have a Markov window of 1, 2? What is it? How many different actions am I going to use in order to predict the next action? Right? So they already knew about the filtering problem, which is this predicting the current hidden state, right? That's the plan structure, right? And then that's what state am I in now, given that things are hidden. And then prediction, which is predicting the next hidden state. So they knew all about these problems, at least in the abstract. So they were doing this kind of stuff, but they never talked about it this way and they never applied it this way. And, so there you go. Okay, that is a whirlwind tour of the old work, not the old work, the historical work that you really should know about. And what I said is not by any stretch everything you should know about those papers or the papers that are related to those. And sometimes I didn't even cite the best paper. As an example, it was like the most cited paper or the one I remembered most. And so I highly recommend going back and reading, at least scanning those to understand where we were, where we came from, what the limitations of those systems were, so that you understand where the hard problems actually are. Okay, am I turning it over to you? Okay, I'm going to turn it over to Reuth. There you go. Oh, any questions? No questions. That's the board. This is cool.
Okay, so thanks, Chris. And I will say one thing about a small nod to MDP people. I remember Chris saying that at 2019, and that made me think, how we can use MDPs for reinforcement learning. That's one of the works I'm going to mention, goal recognition as reinforcement learning. So that's also something that Chris said at one of the slides and then became later a paper of someone else. So the main lesson is you've listened to Chris, you publish papers, but
That's not the main.
that's for me specifically, I can tell you that when I started my PhD, I read one of the papers of Chris's that I'm going to mention, and that was the paper that developed my PhD thesis. And I was very lucky that one of the first people authored one of the papers that I started my research from actually became a colleague and a friend later on. I wish for PhDs and students in this room that you have this opportunity to have a colleague with you that you work with that help you this way. But definitely, all of the works that he mentions, and you've seen the enthusiasm, is something that is contagious, and it really helps the good research. So regardless of goal plan recognition, find people who are excited about their work, that when you talk to them, you're excited about their work, because this is key to do good research. Okay, so I hope we were able to convince you so far that goal and plan recognition are interesting problems and difficult problems that are worth exploring. And you want to go and start working on goal recognition. What should you do first? What do you need to have in mind? So we start with just formulating the problem. So we need to ask, what elements do we need for the problem? And to later on in this tutorial, we'll see some examples of how we implement that, and we will always go back to this running example as much as possible by Steve Levine and Brian Williams for a human and a robot collaboration setting where the robot needs to help the person. So we have Alice who's making breakfast, and she has a very
Even more together.
and she has a very great robot that works in a home place, which we are gonna have any second now with the new one robots that we have around, and we're just waiting. It's right there. It's right there. And one of the reasons, by the way, we don't have these robots is because of plan and goal recognition is a crucial part of these entities that we don't know how to do very well yet in live settings like this. So we have the robot. The team needs to make breakfast together before Alice needs to go to work. So they need to make a drink, which is coffee or some juice. And we need to, and for each we have sub actions that we need to execute to be able to perform that. And to eat, the team together needs to either make a bagel with cream cheese or some cereals and milk. So this is a general problem, and you can think about a lot of constraints, and with different assumptions, you would get different specifications of the problem. For example, is it timed? Does Alice need to get out of the house in 30 minutes? How long does everything take? That was the original work by Levine and Williams for temporal constraints on that and understanding doing goal recognition with these constraints. You could think of what happens if Alice needs to make actually 2 breakfasts, or how should she combine things, and how can we recognize if she does more than one thing at the same time? Do we have sensors that help us see everything she does, or if she walks to the other side of the room and the robot is looking the other way, it doesn't see what she's doing, and the robot is missing out on some important observations, so we have noisy observations. What happens if suddenly she does something that is unrelated to making breakfast? And now we have noisy observations that are like external or redundant observations. So given the assumptions, we're gonna have very different problems here. To formalize that, yeah. Great. Can Alice communicate with the robot and help it understand what to do, or does it need to infer everything on its own? So Clippy was a great example of, let's just ask the user, are you trying to write a formal letter? And that was most of the time more annoying than helpful. So we will see that a lot of the work on goal and plan recognition tries to minimize interruptions. Sometimes it is crucial, and there is a line of work, if you're interested in that, on how and when to ask a question to get clarification, disambiguation. But it's not something that is, most of the time, and I'll talk about that as well, most of the time we assume that we need to infer the goal without interference.
For example, Alice is making the coffee and says, yeah, the robot, please do bake for me. Can she give instructions to the robot, not the other way around? The robot asks Alice, oh, should I do this or that?
So Alice can, so here not, you assume there's no communication, you can potentially think about how so all of that talks about the inference of the robot. If Alice just says something, then the robot doesn't need to infer anything. When you talk about teamwork, fluency of the teamwork, you need to think about this. There's always a cost for communication. So for Alice to give instructions every point in time becomes cumbersome. And then you will need, again, goal and plan recognition. But it's definitely, there's another tutorial, a whole day tutorial that you can do just on how to assist better in this type of interaction.
If you stop and think about a lot of those situations, there's a shockingly large amount of things that the robot could do that don't require clarification, that don't require, they can be very, very helpful before they even have to engage the user. And maybe they'll just be helpful, they'll do the right thing, the user will finish it off, and then you didn't have to have the conversation at all. So there's very much, as Reuth was saying, there's very much this weighing that you have to do about the value of talking versus the value of not talking, especially depending on how good is your plan recognition algorithm.
Okay. More questions? Okay. Okay, so when we want to formalize such a problem, we need to have an environment. We have the actor, the acting agent, we have the observer agent, and we have the actor observer relationship, which is related to what we talked about. How can they communicate or not? Our focus is on recognition of a single agent, which is another thing that we can talk about in open work more. How to recognize the goals of a team and different teammates within a team. So it's still considered a multi-agent systems problem because you have two agents, but we look at it from a concentric perspective of one agent trying to infer the behavior, the actions, the intentions, goals of the other. So we start with defining the environment. It describes the dynamics of the settings in which the actor operates in. Often it is called a domain theory. This is a name that is common a lot in planning as well. So it's been very useful when people started using planning for goal recognition. Then suddenly the word domain theory became very common to use that. So we have the state space of what is currently available in the environment. We have the oranges, we have the coffee, we still don't, or the beans for grinding coffee, we still don't have coffee. Once we grind them, we have coffee. We have the initial state, the set of actions that the actor can do in the environment. Notice that here we assume that the observer is a passive entity. It doesn't do any actions on its own, and I will mention a bit of work on interruptions, active goal recognition. There's some work on that, but the basic fundamental problem of goal and plan recognition, the observer is not an actor. It doesn't act in the environment. It senses, observes, and infers. So the actions that we see here are the actions observed by the robot in Alice's case, that Alice acted in the environment. So these are Alice's actions. They can be deterministic or stochastic in the sense of the acting agent. There might be different outcomes to what the agent is doing. We might have temporal actions, like we've mentioned, that something takes longer than something else. The transition function defines us what happens if we're in some state, we took some action, which state will we end up in? Potentially, if we're in a Markovian world and have the Markovian property, then we just need to look at the state that we're in now and the next state, and we know what is the outcome of the action. For non-Markovian worlds, which are very important in plan recognition often, you need to recognize not just from the current state, but a sequence of past states that you've been in. And then the transition becomes more complicated. The set of possible goals, this is also the initial state, but also the goal states. It's a set of labels of what the agent might be pursuing. So in one sense, you can say, okay, in Alice's case, she's trying to make breakfast. We have one goal, but that's not an interesting goal in plan recognition problem, so we want to make it more interesting. So we can say that there are different types of plans that she can do. She can make orange juice and cereal. She can make orange juice and bagel. She can make coffee and cereal and coffee and bagel. So now we need to recognize between these four. Yeah.
Regarding the transition function, deterministic expression, what meaning the second S?
Yeah, I think it's a copy from the other. It should be SX goes to S. You're right. Yeah, it's the standard one that you're familiar with, MDP. Yeah. So the key here is that in most, and this is another open problem we can talk about later, in most plan and goal recognition algorithms that we currently have, you assume you start with an already predefined set of goals. This set can be huge, it can be infinite, but you need to have a clear boundary of what is a goal in the environment. And when you get that, and you know the current state, and you start observing and getting observations, you need to infer what the actor is doing, what Alex is doing in the environment. Does this make sense? Okay. Question? Okay. So in continuous domains, action transitions from one state to another via paths through the state space. And that means that, for example, in planning, we can use PDDLs to have actions that transition from one state to another and understand that. And we'll see later some works that do this. In non-deterministic domains, when we do plan recognition, we are actually doing policy recognition in a sense, or contingent plan recognition, because there might be different paths coming up ahead. If we talked about the fact that we need to predict also what the agent did so far and what they're going to do next, potentially, even if so far the observations are linear, we only seen action A, B, C, D, or state A, B, C, D in the environment that changed. But when we do plan recognition and we need to predict what's going to come next, we potentially need to also provide branching of the plans. If Alice made cereal for breakfast and she's now either making coffee or orange juice, but she tried to squeeze oranges and the orange, or she opened the orange basket and the oranges have gotten bad. So now she needs to make coffee. The fact that you have this branching, if else, means that the prediction for the future potentially needs to hold more than just a linear plan. So in non-deterministic domains, we also need, for plan recognition, we also need policies. So an environment induces us a set of plans or policies that represent the set of possible behaviors that we will see, that we might see in the future. Yeah.
Do you differentiate plan from policy?
Policy. So when we say plan, usually we refer to a linear sequence. So I'm taking one action, then another, then another. A policy,
Potentially with hierarchical structure.
yeah, potentially with hierarchical structure, but it's deterministic, and we can check mark and progress along either the sequence or the pyramid. In a policy, we might reach a point where we have a decision point where we might do this or that. Something might happen or not, and then we might need to describe more than one action ahead. It's so basically that's yeah.
Can you imagine a world where some of the actions have to be taken, but their order doesn't matter
Yes,
in a deterministic environment?
yes, that's correct.
Is that
So you need to be able to model the fact, and we'll talk a lot about works that have partial ordering. In grammars, by the way, for example, when we speak, especially English is very structured. We always say compared to other things. Yeah. So we know that the verb comes before the subject, or the subject is before the subject and the verb. In other languages, it is more flexible. In goal plan recognition, it's all over the place. Most of the time, what we do is not fully structured. So we need to be able to capture that. That's true. That's a good point.
And do it efficiently.
And do it efficiently, yeah. Okay. So in our running example, a state specifies the positions of the objects, whether we have a cup, whether the already have orange juice or not. The actions represent the activities performed by it. In our case, is the human. It's Alice's actions that we're trying to observe, and the actions are deterministic. So in a probabilistic version of the problem, we might fail in some probability. The Alice might fail in some probability, and we'll have to account for that. So now we are moving on to talk about the actor in the environment, which is, in our case, is Alice. So when we want to, there are some assumptions that we need to identify and clarify before starting to work on this formalization. What does the actor know about the environment? What are their capabilities? What do they know? So the set of actions, even to define what set of actions are available, is something that depends on the user's capability and its own sensor model. If Alice doesn't know we have oranges, she won't think about making orange juice. So we need to understand what Alice knows about the environment. For simplicity, often you assume that the actor and the observer have the same knowledge about the world. But what happens if not? And there's some work on that as well. But the simple case, you assume both of them have the same observability. What are the agent's capabilities and preferences, the actors? Can they compute an optimal plan? It's one thing to make breakfast, but if we're talking about a sophisticated hacking attempt, that requires recursive reasoning, the attacker will try to deceive us by doing something. But if the attacker knows that we know that they're sophisticated, they might not do that actually, or do something else. So you potentially need to have recursive reasoning or not, and you need to have a model of what is the recursive reasoning level of the other agent and what are their capabilities and preferences. If you know that Alice prefers orange juice over coffee, then when you have probabilistic models, you have very strong prior now. Potentially, a lot of the plan and goal recognition would be helpful, but most of the time it would be very easy. She makes orange juice. Like, this is what she usually does. What is the relationship with the observer? Like we said, are they teammates or is it an attacker? Is Alice aware of the robot trying to help her or not? And more. So all of that are things that we need to have identified even before we start writing any formal notation. We need to ask these questions. Generally, when we talk about the relationship between the actor and the observer, we have three different types of recognition. We have keyhole, adversarial, and intended. As I mentioned, we have a 2.5 hour long tutorial. That's not enough to cover everything that we want to tell you. So if you have questions or you are interested in something else, let us know. We can also refer you to relevant papers later on. Intended recognition, because it's easier, most of the work I'm going to talk about today from the approaches types that we are going to look at are keyhole recognition, which is it's assumed that the observer looks through the keyhole at the actor and tries to infer without any communication between them. If you add something more, it becomes more complex. And also in this model, it's shallow in terms of the reasoning. You also assume that the actor is indifferent of the fact that the observer might try to help. So if we look at Alice and the robot, Alice acts in the environment as if the robot is not there. Potentially, if she would do this, it signals the robot, fetch me this, right? It makes sense. Or she would signal somehow of the fact that this is her plan, so the robot can help her, which is intended recognition. The actor explicitly tries to help the observer understand. But then you need to think about the fact that the actor knows that I'm trying to do something. So if they don't signal very strongly about something, then maybe they're not pursuing that. Yeah.
So talking about like the actor and the observer observes what the actor does.
Yeah.
And we want to infer the plan.
Mhm.
But at the point where then the observer tries to help the agent, then is it possible that the plan might change of the agent?
Yes.
Because as soon as I'm reaching for the orange or whatever, and then the robot helps, I'm not reaching for the orange anymore because this is not part of my plan.
Yeah.
Right?
Yeah. So this is something that you need to incorporate, how to update your belief states given that things have changed in the environment, and assuming that whether Alice retracted the hand because she realized you might be trying to help by fetching an orange, so she doesn't need to do that, or she's not even interested in an orange juice, but now that she fetched the hand and you think that, so now she'll do something completely different to signal you, no, this is not what I wanted to do. And this is team fluency. There's a lot of work on that because it becomes very complicated and requires theory of mind. The intended recognition part is something we won't talk a lot about today.
You can even get cases where people adopt new plans because of the thing you did in order to help them. I don't
Yeah.
want orange juice, but oh, hey, robots getting orange juice. I will suck it up and deal with the orange juice today. That's it. Then I don't have to get my coffee. That'll be okay. I'm busy today. Rather take the orange juice. So it can get very complicated.
Yeah. So for now, we simplify. We assume most of and adversarial is even worse in that sense, because now we're also trying to hide the actor tries to hide their intentions and potentially deceive, intentionally do something different, and then you need to balance the costs of deception versus acting legibly.
We'll have to argue about whether or not it's actually Parker.
It would,
I think that's an interesting question.
Yeah.
Sorry.
so now in terms of representation, we're going to look at in most of the works we're going to talk about today, we're going to look at a very shallow approach of keyhole recognition. We have two actors in the environments, but they don't talk to one another. They don't communicate. They are not trying to convey. Alice doesn't try to make the robot understand what she's doing. The robot needs to understand that. So this is our foundational approach here that we'll use. So as I mentioned, we need to identify the assumptions that we have. And like we said, the actor's behavior may be influenced by the relationship. So again, we are very careful right now to talk about keyhole recognition, not to make this too complicated for now. Again, there's work on that as well. If you're interested, let us know. So now we want to formalize the robots part of this, the observer. So we need to look at how does the recognizer perceive the actor's behavior? What is the recognizer's sensor model? Again, in most of the basic work the most basic assumption you can make is that both of them have the same observability. But again, what happens if Alice does something that a robot doesn't see, like from a point of view that it can't see? Now, from an actor-centric perspective, it's different than an observer-centric perspective, what's going on in the environment. So it makes the problem more complicated. Right now, we are not looking at that too much. In terms of the recognizer's objective, again, if we are trying to be a helpful robot in the kitchen, it would make the problem different than if we were trying to identify faults or attacks. And we can also potentially intervene. Can the recognizer interact and affect their behavior? And we're going to talk about that later. And again, to begin with, we assume not, and then we're going to add that as well. And I'm going to mention some work that does that as well. So the type of observations we get, the observer gets observations. It has this domain theory we talked about and potentially a set of goals and what it knows generally about the environment. Now we're starting to get sequence of observations. What are these observations? That depends on the sensors of the recognizer. Usually in goal and plan recognition, which are the main classes we are talking about today, these are symbolic actions or states. So either we observe the action itself, we can, using activity recognition, we have a classification. This is actually picking up oranges. This is actually grinding coffee beans. And then we take these actions and we generate an observation sequence from them. Or we get a set of states, because you don't see a person squeeze the orange necessarily. You see that you've had oranges and suddenly you have juice at the bottom. So there was one state, now there's another state. The activity itself is sometimes not observable. You only see the outcomes. And then you have states that need to be mapped into observation sequences. So you need to identify that and choose what type of sensing capabilities do you have as the recognizer. And that defines the three different types of recognitions we've talked about: plan, goal, and activity. So now, when we have a recognition task, whether it's a goal, plan, or activity recognition, it is characterized using the observation sequences that we got. Goal recognition is what is the likelihood of each of the goals from the set of goals we are considering, given the observation sequence that we've observed. Plan recognition is a complete plan. In this case, we use the symbol for policy even. Potentially, we might infer a policy as well for plan recognition, given the observation sequence. And activity recognition is a prediction of the next step or of the current step. Filtering versus prediction. What is A that I care about? Either this one or right one, the immediate one after, given the observation sequence I've seen so far. And as a special case, this mapping can also be deterministic, which makes the problem easier, given that it's not easy, but we'll talk about later. Okay. So, and again, some works focus on probabilistic models, and then potentially it's not just saying this is the most likely goal, but giving you a distribution of likelihood. Maybe two goals are fairly similar in their probability. That would give you a lot more information than this is the goal the agent is pursuing and that's it. So as a general checklist, like a useful tool, that if we are now trying to devise a new plan recognizer algorithm or a goal recognition algorithm, this is the checklist. It's a slide that you're welcome to go back to and look and ask yourself if you have good answers and you are clear about the answers to these questions. That will help you formalize your problem better and also understand which type of work should you look at to solve it. Okay. If you're making a new contribution, one more thing I want to say. You can devise a new algorithm from scratch. there are new approaches every so often, every 5 years or so. There's a completely fundamentally new type of recognizer that is out. I hope I'll be able to cover a lot of these today. But often a very strong contribution is also if you take someone's idea and you make it work better in practice, work better under a new set of assumptions. And this work better can be usually classified into one of two types of contributions. Either you make the representation richer and more complex, so you're able to represent things that are more intricate, or you make the algorithm work faster or more optimally. So all of the works we're going to talk about today fall into either a completely new paradigm or they do one of these. So again, we don't have too much time today, so I'm not going to talk more about that. We did elaborate on that in the book if you're interested, and you can talk to me if you want to understand more about the differences here. Thanks again for being here today on the first day when half of you are still jet lag. So I really appreciate that and that you're staying so long. Now we're gonna talk about, I hope we were able to convince you before the break that goal recognition, plan recognition are fascinating problems, difficult problems, and we have a general sense of how we are formalizing these. Now I'm gonna talk for the rest of the time I have today, before we talk about open problems, about how people have addressed this so far in more recent years, and giving you a bit of an overview of like a taxonomy of what exists. If you are working on a problem and you need recognition, most cases that most of you at some point in the pipeline of what you're doing or what you would like to be doing need a recognizer. This is why you're here. So understanding which recognizer off the shelf you might want to use, or which recognizer you might want to take and modify a bit, that will give you a sense of at least where to look at, because the number of papers we could have talked about here today is huge. We needed the whole conference. Like I have a semester-long class where I talk about goal and plan recognition. So there's a lot of work out there, and you don't want to reinvent, like Chris mentioned, something that someone already worked on. Okay, so as a reminder, I'm sorry, is this better? It's not better. Okay.
There you
Yeah. So in terms of the solution types that we're looking for in a recognition problem, when we talk about a plan recognizer, we can output a plan, which is a sequence, state action of transitioning from one state to another, and this is what's going to happen in the environment. And recognizers that try to generate these types of plans are usually using either deterministic planning, constraint satisfaction problems, things that are deterministic and are in that sense more suitable to this type of representation. If what we're trying to do is recognize a hierarchy of basically, these are the basic level actions of what I observe in the environment. All of these actions are related, for example, in the Alice and the Robot example, all of these are related to making a drink. All of these are related to making food. And both of them together are related to making breakfast. Now I have a pyramid shape. So if this is what I care about, and abstraction levels of the plan that the agent might be pursuing and where the agent is across this pyramid, then we are looking at hierarchical planning, we look at parsing. These are the types of dominant approaches that we'll see. If we're looking at stochastic environments, like we've mentioned, that potentially things might branch later on, we might want to look at policies. So we're looking at stochastic planning, we're looking at RL, supervised learning. All of the MDP-based approaches, whether it's RL, supervised learning, learning from demonstrations, IRL, that I've talked about during break with someone. All of that are Markovian, but they don't necessarily need to be. So potentially we might need to consider a history of states before I'm looking at the current most likely state that's going to come next. So we're going to talk about each of these. I've broken the next set of works I'm going to talk about. I'm going to talk about linear plans, and the leading approach is Ramirez and Geffner that I'm going to mention. They are the seminal papers that presented that. I'm going to talk about hierarchies using Chris's work as the main thing, but here we're seeing an example of how does this look like in the Reuth and Gal's work, where you can have different branches and you might be in different locations here. But eventually the actual plan is the nodes that you can reach. It's too little. I'll show you in the later slides, but basically this is the football example where you might be attacking, you might be defending, and what's gonna happen is only sequential. It might be in different ordering, but it's still along that sequence. And then I'm gonna mention some works that do policy learning, and this is an example of an MDP. So no matter what state you're in, you need to consider the likelihood of different states. Potentially after you've seen that observation, either you've seen the action you thought you were gonna see, or you've seen something else, but now you're in a new state and now you need to do that again. And potentially you might have a branching factor there. So these are the types of solution we're gonna look at. In terms of, so I'm gonna talk next about explicit symbolic approaches. So most, as a general like overview, as a field, plan and goal recognition, because it's sequential decision making. It's a multi-agent systems problem, but we're looking only from the perspective of one about the others. It's an inference problem. It is not the mainstream type of problems you would expect to be solved by learning approaches ever since we've started with the modern machine learning approaches, neural network, deep learning, deep RL, now LLMs. All of these types of projects, works, efforts, techniques, they focus on prediction. They're focusing on induction. We're looking at abduction. So they're not easily transferable. And when you, for example, vision had an amazing success, was one of the first domains in which machine learning was very useful, because eventually the prediction is a label and the input is a set of pixels. And you could, in terms of the space size or how you map that, that's something that was easy to generate. When you think about goal and plan recognition, learning is hard, and we'll see that learning became useful in this type of approaches fairly late compared to other works that have seen the use of neural networks very early. Neural networks start to be useful here. I think that the first paper I've seen was 2019. At the time, people knew what's neural network. It was common. Only then we've started seeing contributions that utilize this type of work for goal and plan recognition. So I'm going to talk about learning later on, but this is the next part. But before that, I want to talk about symbolic. And symbolic is a code word for approaches that are not learning based. We assume that we have structure, we have symbols, we have knowledge that is given to us pre-learning. So I'm going to talk about explicit symbolic and implicit symbolic approaches. And I think that the main thing from the book that we published in 2021 and what you're going to see today is the end part with the learning and where we are now and how that was used with learning. So most of the explicit and implicit are things that already were in the book. Some of that was added and updated, but basically the two first components are explicit symbolic approaches and implicit. Okay, so this is the symbolic. Now, what's explicit versus implicit? Explicit delineates what should happen after what and why in a very structured way. So if Alice can make breakfast like we've talked about, these are all of the possible plans she can be making. If she makes breakfast by drinking orange juice and cereal, then she needs to get a cup. She needs to squeeze the oranges. She needs to potentially grab milk, grab cereal, put them together. This is the whole pipeline that we need to consider. And this is how it's combined. Once we have this, by the way, if we see Alice gets one cup and then we see her get another cup, we now has these nice edges between the nodes. So we can say the first cup we think is related to the fact that she's gonna make orange juice. The next one is related to the fact that she's gonna make coffee. And she is making these two together, and I can link each of the actions I've observed to the right goal if she has more than one. So the explicit part of explicit symbolic approaches is meant to provide us with a structure of how this plan is constructed in hierarchical plan recognition. So the first paper I'm going to mention is FAT, Probabilistic Hostile Agent Task Tracker, by Chris and Robert Goldman. And what they did there, basically, they looked at plan recognition as a parsing problem where the recipes can have partial ordering. So if who has taken programming languages, compilation, something that talks about derivation rules? Who of you have seen that? Okay. So a derivation rules decomposes something into a higher granularity. So a sentence is a subject, verb, adjective, verb, something, adjective, subject, verb, something. This is the composition of the sentence. And as I mentioned, in English, most of the time, this is very linear, and you can only have that in a single order. But when we talk about plans, potentially things can have different orders. If I need to make breakfast, I need a mug, I need coffee beans, and I need the bagel. But potentially, I can first have the mug, then the bagel, then the coffee beans. Or I can have the the bagel, then the mug, then the coffee beans. But I can't have the coffee beans before I have the mug, because then when I try to pour in the coffee, it will spill all over. So there is some partial ordering that I need to consider here. The contribution, one of the core contributions of FAT was looking at this partial ordering and efficiently being able to represent that in a grammar. So if you make breakfast, you can recognize that you need to make a drink, you need to make food, but then you also have a set of ordering constraints. What should come before what? And if you didn't put anything here, and this is an empty set, that means that you can do these two in any order that you want. Now, it's not just linear, because this is the plan itself is hierarchical. You need to think about the ordering constraints of parent nodes as well when you're looking at something. What is likely to happen next doesn't just depend on the current specific action you're looking at. It's not Markovian in that sense. You need to look at the ordering of everything, the ordering constraints of everything you've seen so far. What is likely to happen next? So this was a huge contribution, and it outputs a probabilistically weighted set of explanations. What is most likely to happen next? Now, the strong thing about that when you're using explicit symbolic recognition is that if I am a trustworthy robot right now, and I've seen that there's a cup of coffee now, it's not just that I've seen a mug for coffee. I can predict what are the open immediate next steps I might be taking. I can see what are the abstract level states. I know that right now Alice doesn't think about making food potentially at all, but she is gonna need that later on, so I can start thinking about that maybe and help there. I have all of this laid out for free in a sense. After I've done a lot of work in making this representable and to infer that in real time, now I have all the information I need to be a helpful teammate. So the huge gain is the fact that you have everything given to you at the end, and it's probabilistic, so you also get probabilities of what might happen next. And you can generate explanations. I've had some work, for example, I've been talking to financial companies when you need to analyze what other people have done. There are analysts that see the need to read the logs of what people have done. If you're a teacher that needs to understand whether a student understands the task or not, you need to watch the videos of them performing something in an educational software, or you need to somehow get that information. These types of structures give you a lot of information about what happened, when did you bias from something. If you think about medicine and doctors have guidelines that they need to follow. If they shift, you cannot just say that there was a shift. This is not something that makes sense in this plan. You can also say, where did you bias, or what is missing from the plan to work? So there's a lot of information you get from this. Any questions about this, by the way, so far? Okay, so there was some work before FAT in this that Chris acknowledged, but for me, I think that if you are looking at one paper about probabilistic explicit plan recognition, my recommendation is start with this one. If you really don't like grammars and you don't want to look at grammars, another option is SBR. This is a paper, the algorithm is called SBR, but the paper is called Fast and Complete Plan Recognition. Because it's fast and it gives you all the possible plans to an extent of recursiveness, but we're not going to talk about that now. Basically what it does, it says, okay, so here we had to have grammars, and basically for make a drink, now we need another derivation rule for how make drink can evolve, and so on and so forth. And that gives you the ability to handle recursions. It makes it efficient. But if we don't have very complex constraints here, one thing we might do is just write it down. We can write down all of the possible plans the agent might be pursuing. So you can see here we're starting at a root. We might, they use the soccer example. We might be defending, we might be attacking. If we're defending, we will need to position ourselves. We will need to turn. Then either we clear, we approach ball, and we need to do this too before we position. So the dashed arrows giving you ordering constraints that we've talked about earlier. So this is the order that something must happen. But if you have these arrows, it means you either do this or you do that. So to defend, you start by positioning anyway. If you're attacking, you're either positioning and turning, or you're passing. And if you're attacking, you later on plan on scoring. So you will need to do score after. And to score, you need to either position, either turn, or kick. So this is the type of representation that it gives you. And each observations that you see, now that we have this given to begin with, in real time, when the observer acts in the environment, we don't need to, something that I did not mention here is what happens during observation. In practice, when I observe something, I need to take my derivation rules and building them back into a tree structure to understand what happened, which is the parsing tree. If you've in parsing, when you have the derivation rules, which are the building blocks of how things might be combined, in real time you had to this, which is an expensive process overall, especially if you were doing partial observability. Here you don't need to do all of that. When you're in real time and you observe the environment, you just tick to yourself, I've seen someone turning without a ball. Then I'm either here or here or here, because these are all of the options for turning without a ball that are available in the environment. And you keep this bookkeeping of where have you been along the timelines. So at least you know where along this route you might be. And the fact that you bookkeep helps you then consolidate that into a sequence that makes sense. So potentially, I might say that if I've observed someone positioning, but this is the first observation that I see, then, okay, so if they position, they might be defending, they might be attacking, they might be scoring, but I didn't see them attacking before, so they cannot be positioning as part of scoring now. They're not here, and this is why this is deleted, this one. By the way, do you see that from far the end of the room? Do you see at least the text? Yeah, thank you. So this is very quick, and it provides with all of the possible explanations given. If you can represent them in this plan library, it will give you the observation. So it's very good for real-time inference if you can generate this plan graph. Yeah.
So in some of the previous slides, you had talked about partial knowledge. So you said in here, we didn't see them attack, right? But that's
Yes.
different than knowing that they haven't attacked. So
Yeah.
how do you think through that using this paradigm?
So if what I'm looking for is an action that is a precondition for something else, then that's a real bummer. These types of algorithms won't solve it. If it's an action that I could have seen or not, then I can do something with, I can still infer the rest of it. I might be missing something and say, I did not see that. I assume you've had it if you're done. But it is one of the caveats of a lot of the works that we look at. If we've missed observations, especially, and I will say, the more explicit or the more structure you have and you rely on, the more you rely on the fact that this is sound, that the information that you would get would give you what you need. If you relax that, then actually the ones that are more implicit or latent in the way they represent things sometimes are better at handling noisy observations at the cost of being not as transparent and or not being able to help you understand what's going to happen next. So for goal recognition, it's good, but for plan recognition, it's a problem. You can potentially always take into consideration, maybe I've missed something, and then the next action after that is this one. But that exponentially grows the number of hypotheses you need to maintain, because every time you need to think, maybe I've missed something as well to I've seen everything.
Tied in with that is that, and you may not see the coin flip, but there's lots of inference you can do that's very important to do because you didn't see something. The dog didn't bark. And because the dog didn't bark, I know something else, right? And those are plans that are enabled by the fact that you didn't see something, that some other thing did not happen. So it's very related to what you're saying, and you want to be able to, you need to do, there are a number of different solution mechanisms, as it's already said, that you can take to approach that, but you have to be very careful. There's no other way around it. You have to know what your observation model looks like and when you can and can't, and how are you going to capture it.
Other question on this? Okay, so with FAT, once we've seen the first observation, we're starting to grow these derivation trees, these parsing trees upwards. Once I've seen the mug, I already need to understand this is part of making breakfast. So I can derive all of these rules and make everything make sense. This is the root of the plan, of the hierarchical plan. Here I also have the root, but I'm not committing to anything exactly. I'm just marking. But here I have one, then here I have two. Could it be that the agent positioned itself for defend and then turned as part of attack? Given this plan library, this is not likely. So I will need to patch these marks at the end to get coherent explanations of what happened in retrospect. Not all of that is consistent. So the paper is called Fast and Complete. It is not called Fast, Complete, and Sound. Because the soundness part, and they mentioned that, and they have different components. They have HSQ and CSQ, so current state query versus history state query. For the current state, you can always predict, I might be here, I might be here, I might be here for a turn. But if you want a coherent explanation, you need to understand that you can only be here at 2 if you're here at 1 to combine them together to a valid explanation. So this is, SBR is what they call a lazy commitment. It delays the commitment of connecting the dots between the different observations to later on. FAT is very, not lazy, how do you say that? Diligent. It's
Aggressive.
it commits right at the start, and it tells you that if I've seen a mug, I'm already committing to the fact that this is part of making breakfast with a bagel, potentially, not with a bagel, but this is a part of making breakfast, and I will need to make food later on. Let's see. So this is something that I'm starting to develop. And once I've committed to a mug, I know I'm gonna need coffee beans for this specific plan, which is useful if I want to be helpful. So there are benefits for that, but it also means that I need to grow bigger trees very quickly early on. And these trees will carry on with me, and that's costly. So here I don't need to do that, but I can't really tell you what's the valid whole plan until later on, and then I need to do extra processing. So the next paper is a work of mine which was inspired by these two works. Can we somehow do bottom up and top down to get the same output as FAT, where we get these elaborate trees and the compact representation of FAT, but with a at least faster inference than we had at FAT. So here we're only committing ourselves to the tree, to growing a tree, not up until the root level, but only as far as we can have a coherent explanation of what we've seen so far. So if I've only seen a mug, I know I'm making a pot of coffee. How is this mug of coffee goes into the rest of my plans for today, for life in general? I don't know. I don't care. If I'm making this coffee because I'm gonna have a tutorial later on today, I don't need to carry on the tutorial with me when I'm just at the coffee part, grabbing the mug cup. So here I'm only growing the tree given the observations I've seen so far. So first the mug, then the coffee. Now, I didn't see a coffee. I later seen a bagel. Now I need to commit to the fact that I'm also making food. That means that I care about the fact that I'm making breakfast in total. So now I need to grow bigger parts of the tree. So this is Slim. This is again a hierarchical plan recognizer. It is also probabilistic. Like SBR has an extension that is probabilistic. The original work was not, if I'm not mistaken, but can be. And there's additional work on that. And this is Slim. Another explicit symbolic approach is Elixir. So Elixir, Chris, looks at all of this, and he sees that actually the point of commitment is really important, and Slim does nicely, but sometimes I do want more structure. Sometimes I want less structure to begin with, and I need to be able to control this level of commitment that I want to generate. Maybe if I see coffee, I do want to know what's gonna happen next, because when Reuth drinks coffee in the morning, that means that something important is happening later on. So I need to know everything. But if she's drinking juice, I don't care if she's going to the pool or she's going to the gym later on. It's not a tutorial. I shouldn't care about that. So I can have smaller commitments about this derivation. So now we have this combination of compactness and expressibility. And then Chris did something that only Chris can do, and other couple of researchers around the world who are experts in linguistics and use combinatory categorical grammars. If you haven't seen parsing, I can't impress you here enough. these are very hard to learn and very hard and even harder to generate. Because what we have here, it's not a derivation rule like we've seen that breakfast means that we need to, it's decomposed into making drink and making food. We have leftward and rightward derivations for breakfast. So if I want to represent a goal breakfast, for example, it means that I need to make breakfast, which requires me to make food. But what would be missing from here is to make drinks. I haven't looked at this for a long time. I don't even remember how to pronounce that really. But the point here that here I need a breakfast when I see the food. I don't need that when I see the drink, or the drink can come after. And I can structure these grammars given whether I use the direction of the derivation that I'm using back leftwards or rightwards would describe the type of trees I'm committing to in advance. Now, the reason I'm allowing myself to this CCG so much and say how difficult it is because you don't need to worry if you don't like this, because Chris later on generated LexRec that learns this for you.
Oh, that's
So-
like learn.
Oh, LexLearn. LexLearn and then LexRec that builds on LexLearn. So you can generate that and understand and get this type of representation fairly easy. You don't need to be a master in CCGs to be able to use these systems, but it gives a really nice balance between commitment and the structure. And if you went along the route of explicit symbolic recognition, that means that you care about the explicitness, you care about the structure. This whole discussion is about what's important and what's not. Elixir is, in a sense, the algorithm that gives you full control on how you build those grammars, these structures of what's important to you to know when. Does that make sense so far? Okay, great. So if you think that this is what you want, and explicit symbolic approaches are usually the most explainable ones, the ones that provide you with a lot of extra knowledge that you can utilize, but they do require the structure somehow to be given to you. If you're interested in that, learning more about that, using the algorithms, some of these algorithms are implemented and are available here. This is also where you will find these slides at the end, as well as Sarah's website. I need to have that on my website as well, I guess, because so all of that is available for you if you want to use that. And after I talk about each type of approach, classes of approaches, you will have a QR code that you can use and try it out later. So this is explicit symbolic approaches. Next, I'm going to talk about implicit symbolic approaches. So these are still not learning-based approaches. You assume that you get some knowledge to begin with about what might happen in the world, but it's more relaxed. It doesn't tell you necessarily the order or the partial order that things can or cannot happen. You'll need to figure this out yourself somehow. How are you going to figure this out? We give you some constraints about what makes sense or not. So if this is a PDDL, if you're familiar from planning. I have a representation of an action. I have parameters. For example, for making coffee, I need an agent and an object. The condition to be able to perform making coffee is that I need to have the object, in this case a mug, on the table, and I need at the end for it not to be on the table, and I have the new predicate make coffee. I have coffee. I have coffee already. So it gives me PDDL or planning approaches give me preconditions and effects. The preconditions define what might come before another or not. It's not explicit in the sense that it gives me all possible things that I can do in order to reach the point that I have coffee at the end, but it tells me if you want to have coffee at some point, you will need to satisfy everything in these conditions. Or you need to have another action with an effect of making coffee. But that's, you will need to choose between them and then building backwards the type of preconditions that you're going to satisfy. So this is planning. This was crash course in planning. There's a lot more to say about that. But this is the path that you need to go through to get both food ready and drink ready. You need to have some action to make the coffee. You need some action to make the coffee before that. To make the food, you need to have the bagel. Before that, you need to have a toaster. So this is structure, but you need to, you're not given that in advance. You need to plan, use planners to navigate the search space to understand what you have or what you can or cannot do. And this is the work, plan recognition is planning. It's a seminal work, and I think that there was a surge still ongoing, but started around this time, thanks to this work by Ramirez and Geffner. They've done really a foundational approach to be able to address this type using planning, because it is very useful. Even in the name, planning and plan recognition, it makes us feel like, maybe we can use planning for plan recognition. This specific work, the first one did goal recognition, but then they've extended that. And like Chris mentioned, what they've done here is they said, okay, I have planners, I have PDDLs, I have the specification of what might happen in the environment after what are the constraints of doing something, what needs to happen in the environment for an action to be available to me. I can take all of that and utilize that for planning. How do I do that? To plan recognition. How do I do that? I observe a sequence of actions in the environment, and I tell to myself, if I was the actor and I did this, this is the likelihood for me to end up in goal A, or this is the likelihood of me to getting into goal B. So what they did, they are starting here again. We have a domain theory, which is the PDDL, the constraints of the environments, what the transitions, what is likely or possible or not possible. I have a set of goals, for example, either C, I, or K in this case. And I've seen the agent transitioning from A to B and from F to G. So now I'm thinking to myself, the likelihood that the agent is pursuing C is very low, right? Because if I need to satisfy both this observation and this one, that means that I need to go here, I need to go here, and then I need to start going back to C. That's very costly. That doesn't make sense. While if I'm just interested in going to C, I can just go from A to B to C and that's it. So I'm taking the cost of planning from the initial state to the goal with the observations and reducing the difference from working without the observations, or assuming that the observations do not restrict me in completing my task. And I do that for each goal in my potential goal set. And the higher this cost is, the less likely the explanation is to explain what I'm doing. Potentially, if I'm going to I, then both observations are on an optimal path. So the difference between CO and C not O is 0. Does that make sense? What happens when I teach this to students? I ask them, could it be that I get a minus here? That means that C not O is smaller than, that this one is smaller than this one. The plan with the observations is of smaller value of not having to consider the observations. If I done good work to begin with and I have a good planner, that's not possible to get a minus here. Because you assume that if the observations don't limit you in what you can do, the agent is as optimal as it can get. The observations can only make the plan longer, not shorter. So this gives you a good estimation. Complying with the observations gives you a good estimation of how far off are you from an optimal plan. And this is the gist of it, of what they've done there. They also made that a Bayesian algorithm in the sense that they do have priors, maybe between bagel and cereal. Maybe I know that usually Alice doesn't eat cereal, so it's even though both observations are the same, it's much more likely that she's making a bagel, thanks to the prior that I know that this is more likely. So this was a very strong algorithm, and it helped you to use off-the-shelf planners. They did not implement that in 2009. They did extended that a year later. There were some gaps. It was a brilliant idea, really. It was something that was worth publishing in 2009, but they themselves felt like, but it was so good it had to be out there, but they made a much better version of that to 2010 later on. So if you're only reading one paper out of the two, I do recommend the 2010 one. But both of them are available online. So the 2010 one is called Plan Recognition, Probabilistic Plan Recognition using off-the-shelf planners. And the citations and everything is available both on these slides, and you can find them on other places. Okay, so that was 10. Notice a couple of limitations here. So first we talk about the fact that it's only goal recognition. It labels how likely is goal A over goal B. It doesn't tell you anything about the plan to reach goal A or B. It's not that far off, because if you already had to run a planner to reach each of the goals, you have the plans, you just need to keep them. But there might not be the only plan, there might be others. So it only gives you one option out of possible. If there are 10 different optimal plans, one of them, all of them goes through the observations, you're still assuming that you've only seen A goes to B. And you know that I is the most likely goal, but you might still go there from here, you might go there from here, or from here. There are many different paths. So the basic approach here would give you one of them. It might not be the one the agent is actually pursuing, so it's not really good for plan recognition. So you need to somehow have all possible plans that the agent might be pursuing, or at least a diverse set of plans the agent might be pursuing, even if they're acting optimally and all of the observations are not noisy or missing. I still need to somehow represent more than one explanation. And that's what they've done. Shirin Sorabi et al. In 2016. So they've generated plan recognition as planning revisited. And what they've done there, instead of running one planner per goal, they've ran the planner K times. And they tried to get different plans for each of the goals. And now that you have K best plans, so the first option was they've tried two different ways. One was, I'm just taking the K best plans. I'm taking the best one, assuming that this plan is not available to me. What else can I do in the environment to get another very good plan, either optimal or not? And then another, and then another. A different approach was find a plan that is still as optimal as possible, but also as different as possible from the one I've seen so far. And that would give me a broader perspective of what might be possible by the agents. So this is the planner that they ran. They ran it K times, and now they need to compute the cost of a plan, but instead minus the cost of a plan without the observations, I'm adding some penalties, B1 and B2, for observations that I did not see along this route, and observations that I see but were redundant. Because when I have a minus here, what it means is either I was missing observations here or that they were redundant. So I have these two factors that I can weigh in on. For example, I didn't see B goes to D. So that's a missing observation, but it doesn't interfere with the fact that I can infer whatever I need to infer. But still, I would have liked to see that. That would have made my confidence higher. So I penalize for the fact I didn't see it. So their new updated costs give us basically a similar platform is this one with the difference between with the observations and without, but here it accounts for the fact that I might not have seen something, but I should have. Or I've seen something and this is redundant, because in real life, sometimes we see things that are redundant to the plan that the agent is actually pursuing. So they have both of these. The downside of this approach is that it becomes much more costly, because now we don't need to run the planner twice per goal, one with the observations, one without. Now we need to run a planner K time per goal. So it's much more cumbersome. And again, in real time, I see some younger faces in the audience that maybe have done their bachelor's even when machine learning was already a thing. But everything I've talked about so far are not machine learning work. You do the hard work using some inference mechanism, some computational. So computation in real time is hard. It's not that you've trained something and now that thing is frozen. You get inputs and outputs almost immediately. All of the inference, all of the hard stuff that machine learning is doing in its training time, you don't have here. But that means that you need to perform the inference and the computations in real time. So processing time is important. And this is why it was a thing with fat that led to Slim and Elixir. This is why here we are trying to find ways where we can mitigate the costs. So this would give us a rich representation, potentially plan recognition instead of goal recognition. But it would come at a very high cost that now we need to compute a lot of plans. So I've seen an agent walking in the environment. Now I need to start running a planner to generate K different plans per goal the agent might be pursuing. It might be that by the time I can make an informed decision about what the agent is doing, they're already done. So for a helpful robot, that's not useful for me. So I need to make this faster somehow. And then came landmark-based heuristics for goal recognition. If we're already using off-the-shelf planners with all of the good things that planners give us for free, we can also use a lot of the work that people have done in the planning community to make this problem faster. So almost with every plan recognition as planning approach that you utilize, you can augment it with this. This is basically an approach that uses landmarks. Who here knows what landmarks are? Okay, nice. So we have a couple of planning people. For those who are not familiar with planning, if I'm trying to get to the conference, I will need to go through that door. To this tutorial, I will have to go through that door at some point. So if I went through that door, you don't need to worry about everything before that. Or if I did not walk through that door, but I went into a door to another tutorial, that gives me some way to efficiently disambiguate between goals. So the action of going through that door is a landmark. It's something that must happen in every possible plan that involves me being in this tutorial. So potentially to recognize that I'm in this tutorial, I don't need to recognize all actions, I need to recognize landmarks. To disambiguate between me being here and somewhere else, I need to see which landmarks are different and try to find these. So what this work did, it filters. So first of all, the first thing about the landmarks is this is the first heuristic to understand how many of the landmarks in the plan I've already achieved versus how much I haven't achieved. This gives me the first part. And how much is this unique compared to someone else? If I've seen someone going through that door, this is something that happens only in this tutorial. So that's can help me eliminate other goals that don't have this heuristic. How much unique is each landmark? And this is something that I can weigh in. So basically, it's still plan recognition as planning, but now I can filter some of the potential goals away if I see that I'm very far off from achieving any landmark to that goal compared to others. So that was a very elegant and nice work. And as I've mentioned in the beginning, we've had a lot of work that try to make that faster. And the other side is to make the problem more rich, more complex, and still be able to perform recognition. All of the work I've talked about so far assume a discrete environment representation. Either I had labels for actions or I had MDPs with very clear states that were discrete in a discrete environment. The action themselves were discrete in transitioning. But in the real world, often, most of the real world settings that we care about are continuous. So again, 2017, given the fact that we can now use planners, can we use continuous planners to run this type of approach? But now we have a problem. And Moore and Gal showed, I think, I don't know if it's in this work or in a different one, but they have a very elegant proof. They've shown that if we want to use existing algorithms, we need to discretize the domain. No matter what discretization granularity we choose, there will be a recognition problem in which this granularity is not enough. It sounds trivial, but it has a very nice proof in the paper if you're interested. But that makes sense. Okay, so potentially if I might see an observation sequence that would fail me, maybe I don't want to discretize the domain to begin with. Maybe I first want to get the observations and only then discretize the environment. And this is what they've done here. And they used, on top of that, because it's still very cumbersome, 2 different heuristics to make it faster, inspired by mirroring neurons. So that's a concept from cognitive sciences that says that when you see someone reaching towards the bottle of water, some neurons in your mind lit for picking up, just because you've seen someone else does that. We can talk a lot about cognitive science, theory of mind, and how well does that work in practice or not. But Mo was, in her bachelor's, also a psychology student on top of computer science, I think, or transition. I don't remember exactly the story, but she was inspired by that, and she said, can we use that somehow? And that was the inspiration for this line of work. And that was, to the best of my knowledge, the first work in the more modern line of plan recognition as planning that was able to perform continuous plan recognition. Questions so far? Okay. Another way to address continuous environments was by Sarah Keren, who will be here later today. What she was looking at with robots is about waypoint detection and understanding using basic control and using even analytic formulations where the agent might be going. And the transition model that she's using is basically an analytical model of the robot's dynamics and what it might pursue next. And she uses a Kalman filter to do the inference part of it. So this is a very new work. If I'm not mistaken, it's last year's AAAI. So it was very, very nice. And it was a combination also. I think this is one of the few papers that is able to run with real robots. And if you've worked with robots, you know that just deploying that, even in robotics conferences, they accept often papers that are simulation only, because working with real robots is hard. So it was very impressive that they were able to do that. And that is another way to look at continuous state spaces if you have control as your underlying representation that you can use. So it's not planning. This is something that shows you so far all of the papers that we've talked about in implicit symbolic recognition use planners. This one doesn't. It uses a controller, which is, in a sense, it's a planner eventually, but it's a different realm of research, a different type of approaches that are being used here to solve this problem. If you think that what you need is implicit symbolic goal recognition, you are using control, you're using planners anyway. You want to balance between structure and efficiency or the amount of knowledge that you need in the environment. If you have linear plans and not hierarchical ones, then this might be the type of work that you want to look into. And Felipe Meneguzzi, one of the landmark paper authors, has done a fantastic masterclass on plan recognitions planning and extended work on top of that. And it's available online, including code, including slides, everything is online. You can use that. Questions so far? Okay. So now we are entering the elusive part of learning-based approaches for plan and goal recognition. Why is that a problem? Why can't we just, and this was, when I became a professor, that was the first thing every student that I talked about, do you want to do some plan recognition work? The first question I got was, can't you just solve that with a neural network? Can't you just solve that with an LLM with recent years? And I challenge you, please go ahead, try. I would be excited to learn that it's possible or what you can or cannot do. Usually when I ask LLMs things like that, they wander off to give me stories about things they didn't ask. They're not proactive in any way in understanding what might come next. You might look, Rao is here, right? Rao cannot miss AAAI. Subarao Kampambati Rao is a AAAI fellow. He was the president of AAAI a couple of years ago. He has done recently a very nice series of works on LLMs can't plan. Let's put it this way. They can do other stuff. They can't plan. They can't make sequential decision making. If you can't plan or you can't hold the complexity of planning, you can't hold the complexity of plan recognition, because you need plans for that. So it's hard. And in terms of the complexity of the problem, you can't train enough. It's very sparse. And you don't get enough structure from the examples that you see about what might come before, after. All of the symbolic approaches that we've talked about, whether implicit or explicit, gives you some structure about what's likely or not to happen before or after, and what makes sense and doesn't. And with LLMs, when you start asking them, they give you silly things like chop the carrots, turn on the oven, and then they start talking about laundry. They don't have the contextual glue between the different actions to make, they are able to do that when the prediction is likely. But when the prediction is not something they've seen in the past, they don't have any connections between the things that they can use. So they get lost very fast when you're trying to use inference using this type of approaches. Learning is inductive. So you have the prediction, but the prediction depends on what you've trained on, and that's it. So people did use that eventually. It took a lot of time to be able to combine that because it's such a different way of thinking about the world. All of the works that we see now are not learning problems. We're not trying to learn anything. We're trying to infer something. It's different. So how can we use learning? 3 main approaches and all of them eventually boil down. You learn the structure upon which you can then do inference. But you learn somehow this structure. So you can learn an explicit plan library. You can learn an implicit plan library, like we've talked about explicit, implicit, and you can say, okay, I don't care about the structure, I just need the policies. This is the likely policy of an agent that's pursuing A, this is the likely policy of an agent that's pursuing B. So these are the main 3 threads that we've seen in recent years for using learning for plan and goal recognition. I'll show you one of each. So for explicit structures, we have goal recognition using off-the-shelf process mining techniques. What we do here, we use process mining, which is a learning approach that generates process graphs. If you've heard of Markovian chains, there are many ways to do that, where you elicit what's likely from demonstrations, from explanations, and you get these processes of what you might see next. This is a process graph for a specific goal. This is the partial ordering constraints we talked about. It's basically here. All of these arrows explain what needs to come before what. And then when you see in practice, and these are the observations that were used to generate that, I think, for goal C or D. So now when you have this process graph that you've learned from examples, you can just ask, how likely is a specific observation sequence I see now in a plan recognition problem, how similar is this to this process graph for goal A? How similar is this to my graph for goal B? And we take the alignment between the process graph and the other and the observations that I see, and I can match them. Does that make sense? There's more work on this type of approach. There's a survey on model-free goal recognition or model-free plan recognition that covers additional work that does something similar. So you can go and look at that if you're interested, or talk to me after. So this is explicit. Implicit, we're talking about PDDLs again. We need to somehow know what's the constraints of having a predicate being satisfied at the end of a process of an observation sequence. So GRNet learns an implicit plan library. Basically what it does, it gets us, first of all, before we look at the structure, this embedding layer. Every vector here is a set of predicates in the environment, whether they're true or not. So every state of the world, we use training, a lot of training, to create an embedding space for connections between states in the environment to an embedding space. So eventually, if only one predicate has changed, they're closer in the embedding space. But the reason planning is so hard is that sometimes to finish a task, you just need one predicate to be true that's now false. But to achieve that predicate, you're now going on a quest. You need to explore 10 different actions and add predicates and remove predicates and make, in our example for the breakfast, eventually you need to have the predicate breakfast made. That's it. That's the difference between the initial state and the end state. But to get there, you're going through different states. So if you use training and learning approaches, you can create an embedding space that gives you a geometric evaluation of how close or far off one state from another, given the predicates that are true or false in that environment. And once we have this embedding, we get a sequence of actions, and we can create from these actions the changes in the environment. What happened after I done action A, action B, action 3? You get a sequence of states that you can translate to your embedding space. And then using attention mechanism, you can basically create different heads for each possible goal and see which goal is the most likely. And then once you get a goal set, eventually you can use this output that you get here and select which of the goals is the most likely from the set of potential goals that you receive later on. So the nice thing about this work is that it takes all of the complexity of a PDDL that someone sits and needs to write down, and it says, you know what, I forget about that. You're not going to be a planner. You're not going to need to explore the space. You don't need to care about preconditions and effects. You just need to see how close one state is to another. And once you've observed some things in the environment, let's see the distance that you've traveled along this route. and whether this distance makes sense if I'm trying to pursue each of the different goals. Okay, does that? So this is implicit, explicit. The next work, which was the Markov MDPs one. So there was work on plan recognition on POM-DPs by Ramirez and Geffner, by the way, after they finished with traditional planning, classical planning, they said, yeah, let's do that with stochastic planning as well. And plan recognition is planning using MDPs is something that they also have a paper on if you're interested. When this is a work that I worked with two colleagues, one of them is Felipe Meneguzzi from the Plan Recognition Planning, and one is Leonardo Amado, who's now a faculty member at Aberdeen. And what we were thinking is all of this work, and there's so much novelty now that we can use reinforcement learning to learn how agent acts in the environment and to learn policies of an agent. And one of the questions I always got when I started working in plan recognition from people in learning was, are you doing IRL, inverse reinforcement learning? Are you learning the reward function for an agent who's trying to pursue something? And the subtle difference from inverse reinforcement learning and plan recognition is that in inverse reinforcement learning, you get demonstrations, you get examples, you learn a reward function, and then you use that function to do stuff. To do stuff is plan recognition, for example, or planning. Plan recognition starts with the assumption that you know the reward function, you know the things that are generally true about how an agent acts in the environment, but now in practice, you see someone walking, you know that when they walk like this, they're going to the supermarket. So we were thinking, can we use learning to learn what is the probable behavior of an agent who pursues goal A, B, C, D, so on? And this is the learning stage. And then during inference time, once we see this observation sequence, we no longer need to run things. We've talked about the computational effort of running parsers and planners, and all of the assignments, all of the works we talked about so far need this computational at some point. Here, what we do, we compare an observation sequence to each of the policies. We have a policy for goal A. This is a behavior of an agent pursuing goal A. How similar is the observations that we've seen if this is the policy of the agent? And we use different distance metrics, different measures to compare that. So for example, we used max utility. If you've learned of Q function is a reinforcement learning approach that learns a Q value, which is how useful, how good is it for me to take this action if I'm in this state? So using reinforcement learning, I can learn this Q function per goal. I have a different Q function per goal. And now when I see an observation sequence, I go over all observations and I think if I'm in this state and I've executed this action, what is the gain? What is the goodness of this behavior? And I accumulate that. And I do that for goal A, for goal B, goal C, and so on and so forth. And I get an estimation how likely is each of the goals, how good each of the goals is given what I've got. And basically what you want to do here is you want to find a sequence that makes sense. Like you would say, yeah, the Q value of doing that here makes more sense than doing something else. And in practice, we've shown that empirically it works very well. The benefit of this approach, because we don't have this structure, we talked about missing observations. This is an approach that works very well with hidden observations because we don't need to think about what we didn't see at any point. We're Markovian. At any point, we are only looking at how good is action A if we're here now. So that was a nice work that we published recently, and I have a couple of extensions of that if you're interested in that. And this is available in the grlib repository that you can see here. One of the main things we've worked on and will be published at AMAS 2026. It got accepted, but I'll see you in Singapore, in Cyprus if you're going. One of the things that is problematic here is that it's a bit of cheating. I didn't remove computational costs. I just pushed them to the beginning. I need to pre-process a function, a policy for each possible goals. What happens if I have 1,000 goals? What happens if my goals change? Now I'll have to do this all over again. It's nice that in practice, once I get an observation sequence, computation is very fast, but learning these policies takes a lot of time. And that made us introduce the concept of dynamic goal recognition, which means that our set of goals that we need to consider might change with time, and we need to be able to account for new goals very quickly. So using transfer reinforcement learning, using universal functions, using meta reinforcement learning, these are all off the shelves. Like landmarks was useful for planning. Transfer learning, goal conditioned reinforcement learning, meta reinforcement learning are all tools that exist and can be used for quick dynamic goal recognition where the goals change. So all of that is available here already. If you're interested, you can go and check it out. So before I move on to the last section of the open questions, open problems, I want to talk a bit about work that does something beyond recognition, goal recognition or plan recognition. So so far, did I convince you that plan and goal recognition is a rich problem to explore? That there are many different ways to address that? Good. So I've done my part here. So we've recognized the goal of an agent. Great. What do we do with that? Attack, defend, assist, critic. With guidelines for doctors, we might want to give criticism if something is off. Teaching, we want to give hints to students. We want to do something with it. So once we have a recognition problem and a solution, what can we do with it? How can we make recognition problems easier to solve to begin with? So there's a lot of research around the thing that is the recognition problem itself. So in this last piece of this section, I'm going to talk about works beyond plan and goal recognition and how they're being combined. So first, goal recognition design, which is a fantastic work by Sarah, who isn't here to talk about it herself, but you can ask her all about it this evening if you join us for dinner. What she was looking at is, for example, this setting. If we want to monitor where a person is going, and we're starting here, if the person walks left or right, we assume optimality, then that's great. We know that the person is, if they go left, they go to this goal. If they go right, they go here. But this is also an optimal plan for both agents going up. That's inconvenient. And if we do recognition, that means that now we need to carry two hypotheses with us very far ahead. And potentially we can't assist, we can't defend against some attack. Can we maybe eliminate this? So the agent cannot do this. So she formalized the concept of worst case distinctiveness. What is, at the worst case, what can the agent do in the environment that will make me not be able to distinguish between goals? And now that we have this, her problem is not a recognition task, it's an offline task. Given that I have this setting, can I change it somehow to decrease the WCD? Can I make the distinctiveness point smaller? For example, this is a fantastic example. I put a building block here or a wall. Now the agent must decide on the first step, left or right. If the agent is optimal, I know for sure whether they're going left or right to goal A or goal B. So in this paper, she presented WCD and a couple of algorithms for taking a plan recognition problem, designing the environment to get a better recognition problem to work with. And you can, yeah. So it does assume the agent will take the optimal plan. There are extensions to this work that I've not mentioned here, but I can share links. William Yo is here at the conference, done work with stochastic plan recognition, where you might have by mistake done something or non-optimal, and then they compute expected case distinctiveness. So there's line of work that talks about that as well that you can look into.
So I've seen in other things where, for example, an agent may pursue a non-optimal path. If you assume that the agent has to accomplish its goal within a certain amount of time, in other words, it limits its amount of patience, that also introduces an upper goal, or upper bound, I'm sorry, on the amount of stochasticness the agent can introduce into the system before they fail by.
Yeah, so I'll mention Levine and Williams, who designed the breakfast problem to begin with. I'll mention them at the end. They're doing temporal goal recognition, but you're right, most of the work that we're looking in here at all don't talk about temporality at all, in the sense of like how long does it take. We talked about ordering, but we don't talk about Allen's temporal algebra. There are 13 different relations of must come before, immediately before, or sometime before. They might overlap, and all of that you can incorporate that and get a very complicated goal recognition problem as well. But it's a lot of interesting problems to think about as well. And if you add numerical temporal constraints, that's even harder.
So in this example, the agents achieving a particular goal is considered to be binary, right? So it either achieves goal one.
Yes. Yeah.
If the nature of the goal becomes more qualitative, wherein you're not just looking for an agent to achieve a goal, but also achieve a goal with some, there's some qualitative.
So
does WCD still make sense? Because perhaps the middle path.
So it makes sense for, to achieve as much as possible of the whole goals. I'm not familiar with a work that does this. There is a survey on goal recognition design and extensions. So by Sarah as well. So if you are interested in that, you can try and look the survey on goal recognition design. I had a work where I did plan recognition design using the hierarchies that we've talked in the beginning. How can we change these environments to be able to do faster goal recognition, which was inspired by this. So there are, and then you're not only considering one goal, potentially you might be pursuing a couple of goals together, but you need to minimize the whole cost that you would need to think about. So there's a lot of work that extended that. This is just the first one.
Also fundamentally, when you say things, when you say I want to qualitatively tweak with what the goal is, that's violating the assumption fairly strongly, right? Because what you're doing is saying, wait, there isn't a single state. There are states that I like that are goal-ish with some value, right? And there are things that I'm willing to accept as a goal that are less desirable than this optimal thing. And that's brilliant. That is very exciting and really fun, but does sort of fundamentally fly in the face of a lot of the work, of a lot of the prior work on plan recognition, or goal recognition, because you're saying, I can't tell you what the actual goal is. It's over there. That kind of thing.
So in MDPs, you can have a bit of preference as well. The utility function gives you preference. But it's still, you assume that eventually the agent is pursuing either this or that. Yeah.
Hello.
Hi.
Yeah, would it make sense to separate intent inference from an explicit execution gate where uncertainty or conflict yields a formal hold rather than a probabilistic action?
Okay, repeat the question.
Would it make sense to separate intent inference from an explicit execution gate where uncertainty or conflict yields a formal hold, so a stop state, rather than a probabilistic action? Because I used actually ChatGPT to derive a logic called alignment, differentiation, stabilization. This is a tree state with an execution gate where I just see if my action is admissible. And I'm able to bridge actually Windows or any other operating system with this logic, because it's like a pre-logic step to my thoughts. It explains when I think how my action actually is working or how the intent is formed. I can actually explain that. I'm a language teacher at NUS, and I use this kind of thing to actually, I compressed ChatGPT to throw me something out where I could really see, wow, I want to see how our intent is actually formed, or by what gives our action a decisive gate or a decisive role, you know?
Okay.
So
wanna-
just with, because I'm trying to align that with what we talked about so far in the tutorial, it seems like this is an approach for explicit description. You use learning, specifically LLMs, for doing elicitation of the explicit model of what the agent might be pursuing that you later on use for inference, which is the execution gate that you're talking about. So it seems like it's another approach that can do that. I'll be happy to talk more offline if you'd like to see. It sounds like it's relevant to other work that in the environment, and I think you might there might be other interesting stuff to discuss. Okay, more questions on this so far, by the way? Okay, so this was goal recognition design. We talked a lot about, and that's something that comes around a lot. What happens if another agent tries to deceive us? So Pida, Masters, and Sebastian Sardina did not try to address a recognition task. They tried to see how to formulate the concept of deception in goal recognition setting. They're not talking about actor versus observer, in the sense they're not trying to plan for the actor, they're not trying to infer for the observer under deception, but they're trying to formulate a problem in which the actor might be deceiving the recognizer. So they defined a metric called last deceptive point, which is the last point in your plan that aligns between two different goals, that is still consistent with two different goals you might be pursuing before you shifted and revealed your goal. In a sense, it's a complementary metric to worst case distinctiveness. And they use that to formulate different types of deceptions that one person might be utilizing. So here, for example, this one, what they do here, they're walking at some cost. It's worthwhile to deceive, but then they'll have to backtrack to do this. We can do deception up until here. It won't be meaningful for us anyway, because it's true whether we're pursuing this goal or that goal, it would be the same. The LDP happens here. If we pursue beyond that, sorry, it's not the LDP. Beyond this point, every point that we'll take is an LDP, in the sense that it's something that is deceiving the agent. And there are ways, potentially, if we go here from around, we might deceive for longer at some additional cost. And how to do that exactly, and what are the types of different deceptions that we can utilize? They provide a formalization for that in their paper. And they also, using LDP, provide one example that they themselves, they say it's not like a perfect deceiver because deception depends a lot on the costs that you're willing to pay to deceive and what the other agent thinks about your deceptive capabilities. But they are using one example for a deception algorithm to perform from the actor's perspective to do goal recognition that would be deceitful. And again, there's a whole line of research that progressed after this to represent irrational agents that are still truthful versus adversarial agents that try to deceive you, and a lot of work on that. This is, and now I think 2 slides, if I'm not mistaken, a lot of work was about collaboration or interaction. So far, we talked about keyhole recognition in most of the cases. That's great, but in practice, if a person tries to deceive me, like here, then there's some impact to that. If they're trying to help me, there's some benefit to that. If I do goal recognition, it's because I want to be able to explain that something happened this way over another. So this recent paper, toward explainable goal recognition using weight of evidence, a human-centered approach. What they said basically is if this is a plan recognition problem, I can give you the likelihood that you're pursuing goal A rather than goal B or goal B rather than goal A. That's great. I might be able to provide you some sequences. But this is not a type of information that people care about. What do I, as a person, want to know to understand why goal 2 is more likely than goal 1? The fact that I moved here, observation 5, is the important one. Is where there's a gap between going upwards, going right. That's the evidence that would be the strongest for me to understand that I'm pursuing goal 2 rather than goal 1. So the weight of evidence and how to compute this weight of evidence is the way to perform explainable goal recognition. So it's not a recognition task. We're not inferring the goal of the actor. We're providing an explanation for why do we think that the agent is pursuing this goal over another. So the input is a goal recognition task and an output. In this case, they're using, again, plan recognition as planning approaches. And the output of this paper is an explanation for why they think this is a better goal than this one from a human perspective, from how much evidence do we have that this is the right goal and how to present that to people. More variant as well. So this is explainability. How do we provide explanations on top of goal recognition? Can we help? And this was a question early on. Can't Alice just tell the robot do this or do that? Or can't the robot just ask Alice, what should I do next? So surprisingly, maybe not surprisingly, with recent interest in goal recognition, plan recognition, 2 papers, I think, had the same name, active goal recognition. I think that once this one got accepted, this one, they decided not to publish it, at least not under this name. And there are, this is only archived from what I could see. But basically, both of these papers are addressing the same problem, one in PDDLs, one in MDP. So what they're asking basically is if the observer can act to change its settings, its sensings, how can it optimize its actions to improve the recognition process? If the agent can move around, so potentially it can see more, how can it help us do better recognition? And that makes sense, right? A robot that can't see Alice and can't see what she's doing, can't help her much, can do very good goal recognition. So this line of work tries to look at the goal recognition problem, a set of potential actions that the observer can take. So far, we talked about actions of the actor. Now we are looking at actions of the observer. And we ask, which actions should I take to perform better recognition? And there are two papers that talk about this. And there's another one also co-authored by me about the value of communication, assuming that the only actions that an agent can use are questions and ask, what should I do next? When should I communicate? And when should I not? Because sometimes if you just wait long enough, you will know the goal. How long can I wait? Should I wait? If I need to assist someone, maybe I can perform qualitatively, I might perform something that works out for both goals, because by the time they reveal the goal, I'm continuing with my plan anyway. So this is all a line of work about how should the observer act given that it is performing goal and plan recognition for cooperation. Another line of work looked at not just active recognition to improve, active acting to improve recognition, but okay, so now that I have recognized the goal, what do I do with it? How do I combine my knowledge about the fact that this is the goal the agent is pursuing with the best plan I can help? What should the robot do now that it knows that Alice is trying to make coffee? So there are several works that worked on that. Steve Levine and Brian Williams, we started with their example. They presented concurrent plan recognition and execution for human robot teams, and they take into consideration temporal constraints. If Alice has started to make orange juice, we see that there won't be time to make a bagel in terms of the overall time of the plan, so I'll start with cereal and I'll help her making cereal. So they use LTLs. So this was one line of work. Also, this is an example from Freeman and Zilberstein that you can see here. Once that we have a recognition problem as plan recognition is planning, we're already in a planning realm. How do we translate goal recognition to planning? If I want to cooperate, if I want not to interfere, I have my own task, but it's different, but I just want to make sure I'm not disrupting someone else's task. And if I want to interfere, I want to do something to make them avoid reaching their goal. So they formalize these three different types of interactions. And given that you have a goal recognition problem, how can you use that to do either cooperation, in the independent execution, or interruption? And Too Many Cooks is a different kind of paper. They're looking at the overcooked domain. It stems from a cognitive science model that they've used. That's also Bayesian inference eventually. It's very similar to plan recognition as planning in that sense that it infers what's the most likely goal given the sequence of actions. They're using planners. They looked more about different types of cognitive models for that would resemble the way people, humans, are inferring goals. So they had a paper that is called they had a previous paper, I forgot its name, about Bayesian inference, and most of the same authors, and they extended that to Too Many Cooks, in which they are trying to design one agent to help the other agents to work in the environment in a way that will make the team more efficient as a whole. And this is available on MDP using Geib if you've worked with reinforcement learning. So it's very efficient and convenient to work with. It's very nice. And yeah, so to conclude this part, we have gone through a series of works that talk about plan recognition with more structure, with less structure. How can we do that better? How modern machine learning comes into the picture, and as we were mentioned here, LLMs can potentially be useful to do that as well. And then we talked about, once we have recognition, what else can we do with that, or what other problems around plan recognition can we look at once that we are considering that. So for the last part, maybe do you want to replace me?
Dude.
Yeah, I'm starting to
You want it?
yeah. And we're reaching the end. We have 20 minutes or so. I think open challenges in general, it's more also open for discussion.
Yeah.
So we're giving some of the things that we're excited about to learn more, but if you have others that you want to bring up and talk about, we'll be happy to.
I would also, oh, well, if you're gonna step down.
I'm stepping down.
Oh, you're stepping down. So I would also, a nice moment to reflect on what we've done here. The idea was definitely to sort of give you some history, talk about what the real questions, what the formalization problems are that you have to go through when you're actually trying to think about trying to build a plan recognition system of some variety. And then some, pointers to current systems that one can use that have a lot of trade-offs. I mean, that's the nature of what it is to build one of these systems and to try and use them is you have to think about all the different trade-offs that you have. So hopefully, that was a fire hose of different systems and papers and all those kinds of things, but hopefully we've given you that. If we didn't give you that, then I will reiterate our earlier stated position, which is you should immediately run over to the Springer table. Not Springer, Elsevier, Springer. Who is the publisher? I don't even know. And buy our book because the book covers all of this. So and you can take more time and not hear us rant in a wildly compressed and frantic run to cover all the information. So there you go. Okay, I've already seen people taking photos of this. Some of these are addressed. Some of these are partially addressed. Some of them are addressed in some domains and not in other domains. So some of my early work, well, most of my work has been very much committed to this idea about agents pursuing more than one goal. But there's tricks about it, and we talked about this just a little bit at the beginning, which is that if an agent has multiple goals, they aren't pursuing they're definitely not, if they're interleaved, they're definitely not pursuing an optimal plan for either one. They're pursuing an optimal plan for the joint goal. And if there isn't a trivial joint plan for a trivial optimal plan for the joint goal, then you're going to have maybe two optimal plans that are interleaved in an interesting way with a bunch of connective actions that are necessary for the joint goal, but are not the kind of thing that you'd otherwise see. My favorite example of this was in a house I used to own. The laundry facilities were in the basement and the kitchen was not. And if you wanted to do the dishes and do the laundry at the same time, you kept running up and down the stairs. Now, you're up and down the stairs a bunch of times, and going up and down the stairs in those extra times has nothing to do with the fact that I'm doing laundry, because I could have gone down and sat in the basement, just waited for the laundry to be done, or I could have sat in the kitchen and waited for the dishes to be done. But if I'm going to do both of them, I got to go back and forth. So classic example of that. There's some much, much more complex things that you can wind up with. And they tie in with the qualitative goals. They tie in with just having a conjunctive, what old school folk would call a conjunctive goal. You have multiple goals and you don't have an optimal plan for any of them. So there you go. I love the problem of recognition from observations that map to more than one plan at the same time. And this is not ambiguity. This is, I opened the door to the car, and that meant someone could get in, but it also meant I could put my backpack in there. And I had two different goals. One was to get my backpack in there, and one was to get the person in there. And so you can imagine these imagine actions that, well, there's lots of it. We do this all the time, right? When we're trying to make our plans more optimal, is we say, well, I know that if I do it in this particular way, both of these plans have this action, and I know that that action can play both roles fine and not have a problem. The trick is that that's not always true. Right? There are cases where you consume a resource, if let me see if I can come up with a great example on the fly. I should have come up with one before.
Resource aware goal recognition. There's a paper on that.
No, I don't know of anybody who's done it explicitly, resource aware. But I was thinking cookies. My example, I always go to things that are bad for you. If I needed a cookie, if I wanted to have a cookie just to be happy, and I wanted someone else to be happy, it's not the case that the same cookie can be consumed by both of us and everybody be happy. That doesn't work that way. So getting a cookie in that sense only contributes to one of the two plans. It can't possibly actually contribute to both plans because somebody's going to be unhappy when the other person gets to eat the cookie. Right. So that's recognition of observations that mapped to more than one plan. Recognitions of plans executed by a team. This seems really complicated when you first think about it. And it is, it turns out. But there's this insight that makes you think, oh, wait, it's really simple. And then it turns out, no, that's not right. It's really complicated, which is, I love problems like that. So imagine that I've got a whole team. There's a really simple version of this, which is any action done by any member of the team contributes to a plan. And I don't care anymore what those people did. You just label all the teammates are effectively the same entity. And the problem becomes real simple again. I just have one agent. It's a team, but it's just one agent. It's the agent that is the team is doing the thing. Okay, that seems easy. Yeah, problem must be solved. Yeah, sure. I feel real confident. No. Because sometimes some members of the team can do some things and other members of the team can't do those things. Right? And you want to be very clear that sometimes the team is made up of people who are not necessarily willing coalition partners. And that means if you assign certain tasks to some people, you're not going to get a plan that actually works because other people are going to be given tasks they can't complete or they don't want to complete because they're actually antithetical to the plan. The agents don't care that much. So this problem, at first blush, it seems like there ought to be a really simple answer, and it turns out that for some really simple cases there are, and then for other cases there aren't. Another really great example of this, just I thought of halfway through the last example, is cybersecurity. One easy way to think about cybersecurity and plan recognition in that domain is everybody that doesn't like you is on one team. So all of the attackers are doing a thing. And that works. That actually does work, right? It gives you sort of a lower bound or an upper bound, however you want to think about it, whether your metric's high or low. If you saw all of these actions, you would know that in fact, this person is pursuing, or someone could be pursuing a plan that results in your servers being owned and all the audit logs deleted and a denial of service attack against all of your customers. But that's assuming that everybody's working together. Maybe everybody's not working together. Maybe there are 3 teams of hackers that are all attacking you at the same time who have very different goals. And you have to think about that. So this problem of assigning agents to teams in order to understand what the plans of the individual teams are, also, it's another multi-agent thing you just really don't. Yeah. Yeah. There have been people who worked on these, but there are some real subtleties that I don't think are solved. I don't think are solved. Recognition using LLMs. Yeah. So Reuth said some very complimentary things, or about as complimentary as I can be about these kinds of things. LLMs are amazing. They're really cool. They do some really amazing things. You have to do some really interesting things to get them to consistently recognize all and only the plans you actually want to recognize and not have it make up new ones or tell you about things that aren't in the domain that you didn't know about or other things. They come up with wonderfully complex explanations for things. You give them stuff, it's great. And you're like, huh. It also becomes difficult. Those wonderfully detailed explanations don't have the consistent hierarchical structure or the consistent plan structure, or are not guaranteed to have the right plan structure that you want them to have, that actually only has the thing, only has the elements that our domain theory actually already defines. So that can be a real problem because you don't want to make things up. You don't want your plan recognizer just to make up that I've got extra resources that I don't have.
But they do, LLMs do contain knowledge.
Oh yeah.
They contain knowledge. The question is, how can we elicit that?
Yes, exactly. And I think that's an amazing problem and something, if you're interested in that, come yell at me or talk to me, because I've been doing some work recently on exactly that, trying to elicit some of these knowledge. And there's some just utterly cool stuff about how you can get them to tell you things that are likely to be true in the world that you didn't know were true in the world. Like imagine one of my favorite examples that we've been working on or thinking about is if you tell somebody, I want you to, you're standing in front of a building, you've got your favorite robot assistant standing there next to you, and you say, hey, I'd like you to go into that building. I want you to go to the roof and I want you to tell me if anybody in the crowd that's out around here is wearing a blue shirt. Okay. You and I can do that. No problem at all. Robots can't do that because robots don't know what the inside of that building's like. Don't have a map. And it's not just SLAM, because if it was just SLAM, you'd just say, oh, well, I'll get there and I'll actually build a plan when I'm there. But you can't do that, right? You need to be able to stand outside. You want your robot to be able to stand outside, look at it and say, that's a 35-story high rise. My battery's at a quarter. There is no way I'm getting to the roof, right? You need to be able to do that kind of, and that involves inferring a set of plans. That involves thinking about the consequences of what they are, what you're doing, and how that's going to work. And it involves extracting these causal structures about places you haven't been yet that you don't know, and guessing what they're going to be like. And LLMs are amazing at that, right? They're just fabulous for it. It's just, can you get enough formal structure? And they're like 7 other tutorials or workshops at this conference that are all about that topic. So I'm not the only one saying this. Learning related, sim to real meta learning of goal sets. You want to say something about this? I don't think I added this bullet.
Yeah. So I mentioned, for example, if you are using learning-based approaches, you can use whatever exists for learning-based approaches. I mentioned mine, and one of the reasons we've talked fairly a lot about our work is because we've been working with on this type of problems for a long time, and this is why we think we're the good people, the right people to give this tutorial. It means that we ourselves have some work on that. Yes. So this is, for example, using meta learning to learn dynamic recognition that I mentioned. But there are other ways, like now that we have LLMs, that's a different type of learning mechanism that we can use. Transfer learning in general, sim to real, the fact that I was able to learn a model in simulation, how does that convert maybe to do better recognition in the real world without me needing to relearn from scratch in the real environment. So these are all open problems that still exist, and there's a lot of work to be done here. We're really excited about it.
So that's what we think are the open problems, or at least the first 5 that we came up with when we were putting together the slide. Actually, that's not true. We did actually go through more than one iteration of this slide. So that's, if you all have questions or you all have thoughts about other open problems, we would be happy to talk about them. Yeah.
So I have a question regarding like perspective.
Okay.
So if we look at planning and we look at the example we had with Alice and the role.
Yeah.
What is still missing from a planning perspective to implement such a robot?
To implement, okay, so
to do it, like not from a vision perspective, but like from a planning perspective, that we have this robot, it infers what Alice is doing and then nothing in practice.
So the question is, if given the example, the running example that we've had, what is missing from a plan recognition perspective to actually implement that on a real world robot? Yeah. Well, depending on which plan recognizer you're using, absolutely nothing. We were using that as a motivating example precisely because it's a very simple example, right? There are only 4 plans there. And as I ranted at the very beginning of this, if you've got a fixed number of plans, plan recognition isn't that hard. It's just not. There are only four of them, right? There are only four possibilities there, and you can enumerate them all. There's some much more interesting questions, and Reuth talked about these things like when it comes to help, is if I know that making orange juice takes 30 minutes and you have to leave in 35 minutes, and I'm the robot, and I see you starting to make orange juice, one of two things needs to happen. Either I need to take over the orange juice making task so that you can make something else and we can get out the door, or I need to do the second task for you to finish the breakfast, right? So that level of reasoning, once you have the recognized plans, well, there are even stories about how to do that. Does it exist in an integrated system? No. Could it exist in an integrated system? Well, yeah. I did some work, oh God, years ago on a robot that was helping people set tables. And yeah, we could recognize in real time, we could recognize you put down forks, you put down spoons. I will now offer to put down the plate. Now, does that generalize to the entire solution of all problems involving coordination and happiness and help? No, because there are questions about scaling for the number of plans that you need and and how you're going to get all those plans in there. And boy, LLMs, if they could do that in an automated way, that'd make us all so much happier. But that's the level at which that I think we're actually keeping ourselves, or we haven't yet gotten to the place, or why we don't have robots running around our houses doing this for us, is that there's a huge integration task that has to go on there. And then there's some subtle encoding, knowledge encoding tasks that have to go on there. And then there's tying it all to sensors and real sensors in real world with the kind of you will always perform at the right way in the right time in the right place. That's my off the cuff answer to why I don't have a household robot yet. I'm sure there are other things I haven't thought about yet that would, if I thought about them a little longer, I'd be like, oh yeah, wait a minute, there's another problem. So don't hold me to just that set. But that's certainly a sufficient set for us to not have them at this point. So yeah.
Got a question more related to the starter tutorial.
Okay.
Where you describe and define goal recognition.
Yeah.
And plan or policy recognition. Could you tell me a little bit about? I may have missed, but is it possible to do goal recognition without also somewhat generating the plans with policy?
Oh yeah, lots of people do it. I made a comment early on. I very much believe that one person's activity recognition is another person's goal recognition. And so it is more than possible to do goal recognition without ever generating a plan that is covering the set of things that you're doing, or has this much more complex structure.
There's an important point that we forgot to mention this
Oh.
time. We did that last time.
Did we? Uh-oh.
All of this that we talk about is from the perspective of the observer. Potentially, the actor might have a different mental model altogether.
Oh yeah.
I provide an explanation that's PDDL based. People don't do PDDLs. When the person planned to do something, they didn't implement a PDDL and a planner in their mind. So one might argue that most of the algorithms you've seen here don't do the right plan. They give you a plan that's good enough for some purpose that you need.
That is fine, but let's say we go to the navigation task, right?
Yeah.
Other than and the person goes left.
Yep.
I recognize they want to go to the left top instead of the right top.
Yeah.
But and I understand with learning we can do this. We have labels and stuff like that. But how do we define this recognition task? How do we infer that left top is the goal without somehow saying, well, all the plans that go to the left top go to the left rather than right?
Right. Okay. So I'm not sure whether or not you're catching the question in the video, so I will repeat the question. The real question is, can you do goal recognition without doing plan recognition? And I can understand why your intuition says that when you have a grid-based system that you're trying to talk about navigation, but you could think about other domains where it isn't you don't have to necessarily go through all the intermediate states in order to get from one place to another. Imagine that I was talking about something like, well, if my internal representation for the system was something more like a Bayes net, where I just know, well, I saw you buy fertilizer and I saw, yeah, wow. See, I'm still old enough that I go to violent examples when I start thinking about things, and that's a bad thing. You're not supposed to do that anymore. But I saw you buy fertilizer, I saw you buy gasoline, I saw you buy, oh, hey, I can believe I could build a Bayes net that would suggest you're trying to build a bomb without understanding a causal model that says the timeline for doing it is this, that you need to buy more of that, that you're still missing these pieces or that parts, or understanding anything about what your target was and the larger context of the plan that you're actually executing. I just have a lot of evidence that says, yeah, this guy is driving around the countryside buying a whole bunch of drugs, varying varieties. Now I've shifted over, obviously, to drug manufacture, which is also great. But the point being that you're buying all kinds of Sudafed, right? Wasn't that the deal? Anyway, point is, the more examples I see of you buying Sudafed, the more likely I should be that believe that you're trying to build a drug lab. And that, again, doesn't tell me where. It doesn't tell me how you're doing it. It doesn't tell me who else is working. It doesn't tell me all of the things that I would expect out of a much larger plan structure. But yeah, I totally get your intuition that when you're looking at grid navigation, and that's why I try and stay away from grid navigation as a problem, because grid navigation has all kinds of intuitions for us that I think are wildly wrong for the general problem. It's just, you have very strong intuitions about it. And it seems like, well, I couldn't possibly get there without going through this intermediate state. Therefore, must be. But that particular part is exactly the intuition that I was coding up in Elixir with the way in which those trees worked, that Reuth has talked about. Several different systems are saying some observations are more important than others. They have more evidential weight for what it is you're trying to infer. And again, because I talk about violent examples, if you walk into a bank with a gun, you're robbing the bank. That's what's going on. Now, it turns out I can come up, and I honestly can come up with 6 other stories about what you're doing there. But when I said walking into the bank with a gun, everybody in this room, their first prior was, oh, they're robbing the bank. Yeah, sure. This is the example. He's robbing the bank. But yes, but that's the intuition that you're capturing there, or that's the intuition I think that you have very strongly, which is there are some actions that are really, really indicative. And in the grid example, there are a lot of those that look that way because they're on the optimal path. Does that answer the question? Does that help?
Yeah, I'd still be curious to know what kind of forward model you use to do the other inferences. Like, what do you use if you buy drugs to know that you're doing, like,
So, for example, with our Ramirez and Geffner plan recognition planning, you plan an optimal path towards the goal. And you say this is the cost of the optimal plan here, given the observation. But potentially the actor might be, after that observation, might do something completely different. And still reach the same goal eventually by a different path. For example, so you recognize some plan, but it's not a plan that the agent is pursuing. You know what the goal is. You can say that this is more likely. But the plan is not a plan that would be useful if you're trying to assist. So it would be different. I think also you're asking about open goals, that you don't know what the goals are.
I feel like this is an inverse problem, but the forward thing is there's some planner, and then the inverse is like something is being planned, how do the inverse? And I'm just,
Yeah,
the only thing I can imagine is some planner to do the forwards.
so
Well, okay, but right. So what you have, it sounds like to me, and is the very strong intuition that plan recognition as planning is obviously the right thing to do here. Right. So imagine that instead of that, I have very strong intuitions about how plans are structured that I don't have a planner for. I don't have an algorithm for actually generating. Like, again, I go back to a Bayes net, right? A Bayes net doesn't produce a plan, but I can imagine producing Bayes nets very easily that will tell me the goal that someone's engaged in. That, Clippy, did you open this? Do you have this document open? Yes. Do you have this pull down menu open? Yes. Have you previously deleted 6 characters? Yes. Oh, you're probably trying to erase your entire document or something like that, right? And it doesn't have to do with, because those are all unordered with respect to each other. They're not even causally linked in any meaningful way. So it's not planning in the kind of conventional way that you would think of. It's more like these things are highly correlated with the thing you're trying to do.
That's then data driven, or somebody's just typing in all those these under these conditions. Like, where do you get that model?
Ah, that's all about learning the model. And we'll have to talk about that. We can talk about that's a whole nother tutorial. Happy to talk about it. Reuth talked a little bit about it, and
Mark. Using LLMs for eliciting planning models.
Yep.
That's a, if
Yep.
you're interested, that's a nice leeway to get to this.
Yep.
Thank you very much.
Yep, not a problem. Okay, we are at 12:35 according to my watch, and I don't see a clock on the computer. So I think we're done, but I think I can reasonably speak for Reuth that if you have any questions, you just see us roaming about the conference. We're happy to answer questions afterwards. And, hope this was helpful. And thank you all for attending. And thank Reuth, because she basically organized this whole thing.